Imagine you are holding a bathtub, not a small one, the largest bathtub you have ever seen. Now imagine filling it with water. Not a cup, not a bucketful, all the water in the world's oceans, stacked and compressed into a single, perfectly rectangular container. Now place a planet inside it. It floats. Saturn, the sixth planet from the Sun, the second largest world in our solar system, a planet so massive that 700 Earths could fit inside its belly, would float on water like a rubber duck. Not metaphorically, not approximately, literally, physically, undeniably float. If you could find a bathtub large enough, Saturn would bob at the surface like it had no business being a planet at all. That single fact should stop you cold, because it means that Saturn, despite being 95 times more massive than Earth, despite being so large that it takes light over an hour to travel from its surface to ours, despite commanding a gravitational empire of 146 moons, is made of almost nothing. It is a colossus built from ghost material, a titan assembled from clouds. And the moment you understand that, you realize something important. Saturn is not like other planets. Saturn is not like anything you were taught in school. Saturn is, in almost every meaningful way, a planet that shouldn't exist. But it does, and it has been quietly dominating our solar system for 4.5 billion years, shaping orbits, sculpting debris fields, guarding inner planets, and harboring mysteries so deep and so strange that the greatest scientific minds on Earth are still working to unravel them. Before this documentary is over, you will understand why some researchers believe Saturn may be the single most important planet in our solar system, not just for astronomy, but for the existence of life on Earth. You will meet moons that hide oceans warmer than you'd expect, geysers shooting water into the vacuum of space, lakes of liquid natural gas the size of countries, and a geometric shape sitting at Saturn's North Pole that no one has been able to fully explain for over 40 years. But we begin here, with a planet that floats, with a world that breaks the rules before it even gets started. Saturn spins fast, ferociously fast. Its day is only 10 hours and 33 minutes long, meaning Saturn rotates almost 2.5 times every Earth day. At that speed, the planet's equator is whipping through space at over 35,000 kilometers per hour. The forces involved are so extreme that Saturn doesn't look like a sphere. It bulges visibly, measurably, dramatically. Its equatorial diameter is more than 10,000 kilometers wider than its polar diameter. Saturn is, in the most literal sense, fat at the middle. It is the most squashed, the most oblate, the most visually deformed planet in the entire solar system. Yet for all that violent spinning, scientists still cannot agree on exactly how long Saturn's day is. Not approximately, not to within an hour. They cannot agree, because Saturn has no solid surface to track, no continent, no mountain, no fixed landmark. Just layers of gas merging into liquid merging into something denser still, all of it rotating at different speeds depending on the latitude. The planet's interior spins differently from its exterior. Its atmosphere spirals at speeds that vary from band to band. Saturn's day depends entirely on which part of Saturn you're asking about. That problem alone, something as basic as the length of a planetary day, has occupied some of the sharpest minds in planetary science for decades. Now consider this. Saturn doesn't just reflect the sun's energy back into space the way most planets do. It generates its own heat. Deep inside this impossible, floating, rapidly spinning giant, something is producing energy, radiating out roughly 2.5 times more heat than Saturn receives from the sun. Saturn is glowing from within, not like a star, not from nuclear fusion, but from processes that took scientists a long time to understand, and that connect to one of the most alien weather phenomena in the known solar system. We'll come to that. And then there is the magnetic field. Every planet with a large metallic core and sufficient rotation generates a magnetic field through a process called the dynamo effect. Earth has one, Jupiter has one, Saturn has one, but Saturn's magnetic field is almost perfectly aligned with its rotation axis, a tilt of less than 1/100th of a degree. And that, according to the fundamental physics of how planetary magnetic fields are generated, is essentially impossible. A working dynamo requires asymmetry. It requires the magnetic and rotation axes to be offset. Without that offset, the field should collapse. Theoretical models say it cannot exist in the configuration we observe. And yet there it is. Saturn's magnetic field doesn't care about our theoretical models. Long before any of this was known, long before spacecraft or radio telescopes or even the invention of calculus, people watched Saturn with naked eyes and felt something. The ancient Babylonians tracked it. The Greeks named it for their god of the harvest, Kronos, Father Time. The Romans called it Saturn, god of agriculture and time. And there was something appropriate in that name, because Saturn moves slowly across the sky, the slowest of all planets visible to the naked eye. It takes 29.5 Earth years to complete a single orbit of the Sun. To ancient people watching the sky across their lifetimes, Saturn was the boundary, the edge, the final visible world. Everything beyond it was darkness. When Galileo Galilei turned his primitive telescope toward Saturn in 1610, he saw something that made no sense. The planet appeared to have two companions, two blurry masses on either side, like ears or handles. He wrote to a colleague in code, worried about being scooped, and described it as a triple planet. 2 years later, he looked again, and the companions had vanished. He was bewildered. He reportedly asked whether Saturn had devoured its own children, referencing the myth of Kronos consuming his offspring. What Galileo didn't know, what no one would know for another 45 years, was that his telescope simply wasn't powerful enough to resolve the rings. And in 1612, when the Earth passed through the plane of those rings, they had appeared edge-on, nearly invisible, and then seemed to disappear. It was a Dutch astronomer named Christian Huygens who finally, in 1655, correctly described what Saturn was surrounded by: a disk, a flat, thin, continuous disk of material encircling the planet at its equator, touching nothing, floating in space, held in place by gravity, a ring. The most famous feature of the most famous-looking planet in the solar system had been hiding from us for 45 years, disguised by the limitations of the tools we used to look. And in many ways, we are still discovering what lies hidden behind what Saturn shows us at first glance. This is a planet of secrets, some ancient, some new, some solved, some stubbornly unsolvable, and we are only just beginning. Every story has a beginning. Saturn's begins in violence. 4.5 billion years ago, there was no solar system. There was only a cloud, a vast, cold, slowly rotating nebula of gas and dust, mostly hydrogen and helium, seeded with the heavier elements forged in the deaths of older stars. A cloud so enormous that light would take years to cross it. A cloud that had existed, largely unchanged, for millions of years. Then something disturbed it. Perhaps a nearby star exploded, a supernova sending a shockwave rippling through the cloud, compressing some regions, causing local density spikes. Or perhaps the cloud simply reached a tipping point after eons of subtle self-gravity. Whatever the trigger, a region near the center of the cloud began to collapse. Material fell inward, spinning faster and faster as it went, the same physics that make a spinning skater speed up when they pull their arms in. Conservation of angular momentum, the universe's most reliable choreographer. Within a few million years, the center had become hot enough to ignite. A star was born, our sun. The leftover material formed a disk swirling around it, the solar nebula, a flat plain of gas, ice, dust, and rock, the raw ingredients of everything that would eventually become the planets, moons, asteroids, and comets of our solar system. And in that disk, in a region roughly 9.5 times further from the sun than Earth would eventually occupy, something remarkable began to happen. The process of making Saturn is still debated. The most widely accepted model is called core accretion. In this model, small particles of rock and ice in the outer solar nebula collided and stuck together. Over millions of years, these clumps grew into larger bodies, planetesimals, then into something larger still. A protocore, maybe 10 to 15 times the mass of Earth, composed of rock and ice. Dense, solid, compact. And then the critical moment. When a solid core reaches roughly 10 Earth masses in the outer solar system, where temperatures are cold enough for abundant hydrogen and helium gas to exist in solid or liquid form, something dramatic happens. The gravity of that core becomes powerful enough to trigger runaway gas accretion. The surrounding gas disk begins falling onto the core in an accelerating cascade. Material pours in. The planet grows not gradually, but explosively, accumulating thousands of times more mass in a geological eye blink. In perhaps just a few million years fast by planetary standards, Saturn had grown to its current size, a Colossus, an almost star that never quite crossed the threshold. But here's where the story gets stranger. There's an alternative theory, one that some scientists favor for certain large gas giants. It's called disk instability. In this model, a dense region of the solar nebula becomes gravitationally unstable all at once and collapses directly into a gas giant without the intermediate step of building a solid core first. Faster, more dramatic, and completely different in its implications for what Saturn's interior looks like today. We don't yet know with certainty which model gave us Saturn, possibly some combination of both. But the real complication, the part of Saturn's origin story that reads more like an adventure than a textbook, involves its older sibling, Jupiter. Jupiter formed first. It almost certainly had to. Jupiter is more massive, and core accretion favors the regions of a disk with the highest material density, a line called the snowline or frost line, the distance beyond which water ice could exist as a solid. Jupiter formed just outside the snowline in the richest part of the disk. Saturn, forming further out, had to work with less material. It grew more slowly. And then something happened that reshuffled the entire solar system. The Grand Tack hypothesis, developed by a group of astronomers in 2011, proposes something breathtaking. In the early solar system, Jupiter did not form where we find it today. It formed closer in, and then as it interacted gravitationally with the gas disk, it began migrating inward, drifting toward the sun, moving through the inner solar system like a wrecking ball. Everything in its path was either destroyed, ejected, or crushed into the asteroid belt. Jupiter was going to consume everything. Then Saturn caught up. As Saturn migrated inward through the disk, it approached Jupiter, and the two gas giants entered a gravitational resonance. Their orbital periods locked into a simple ratio 2:3, and that resonance did something remarkable. It reversed their migration. Suddenly, both planets were being pushed outward, away from the sun, moving back toward the outer solar system. Jupiter performed what astronomers call a tack, like a sailing ship changing direction. Together, Jupiter and Saturn retreated outward, eventually settling into the orbits they occupy today. The consequences of this were staggering. The Grand Tack explains why Mars is so small. Jupiter's inward migration scattered much of its building material. It explains the structure of the asteroid belt. It may explain why Earth received just the right amount of water-bearing asteroids from the outer belt, enough for oceans, not enough to drown the planet. It may, in other words, be one of the reasons that life on Earth was possible at all. Saturn went on a journey through the young solar system, and the journey changed everything. But here is one detail about Saturn's birth that tends to stop people when they first encounter it. The rings don't come from the beginning. When we picture Saturn, we picture those rings, those impossible, perfect, shimmering rings. They feel essential, ancient, permanent, like they have always been there and always will be. But the evidence now strongly suggests that the rings formed far later than the planet itself, not billions of years later, but perhaps only 100 to 400 million years ago. In geological terms, that is very recent. The dinosaurs were already on Earth when Saturn may have acquired its rings. Where did they come from? What event, so late in the solar system's history, created the most famous structure in our cosmic neighborhood? That answer is coming, and it will change how you see those rings entirely. First, though, you need to understand just how large this planet really is, because no matter how many times you've seen Saturn in a photograph, you almost certainly do not have a true sense of its scale. Nobody does, until we try to force the comparison. A world so large, it defies imagination. Numbers are slippery things. We are comfortable with the numbers of everyday life, the distance to work, the number of steps in a day, the height of a building. But when numbers grow large enough, the human brain quietly gives up trying to feel them. They become symbols rather than quantities, placeholders for something we cannot viscerally grasp. Saturn lives at the far end of comprehension. And so, rather than throwing numbers at you and watching them slide off, let's try something different. Let's build Saturn from scratch. Start with Earth. You know Earth. You've lived on it your entire life. You know how long it takes to fly across a continent. You know the feeling of looking up at a mountain and feeling small. You know the scale of the ocean. That's Earth, your baseline, your reference point for everything that follows. Now line up 9 of those Earths in a row, side by side. That's the diameter of Saturn's equator. 9 Earth widths, just under 116,500 kilometers. If you were driving at highway speed around Saturn's equator, the journey would take nearly a century. If you flew in a commercial jet non-stop, your great-great-great-great-grandchildren might be on board for the landing. But diameter only tells part of the story. Volume is where Saturn's scale truly overwhelms. Inside Saturn, you could fit 764 Earths, not stacked along one edge, crammed inside the way you'd fill a jar with marbles. 764 of them, more than 700 Earth-sized worlds, all tucked within the belly of a single planet, and still Saturn would have room to spare. And yet here is where the paradox returns. That enormous volume is filled with almost nothing. Saturn's mass is only 95 times that of Earth. When you divide its mass by its volume, you get its density. And Saturn's density is 0.687 grams per cubic centimeter. Water is 1. Saturn is less. You could pack a cube of Saturn into a box, drop it into the ocean, and it would float, every bit of it, the whole planet. Now let's talk about the rings. When we say Saturn has rings, the brain tends to produce a mental image, a planet with a couple of decorative bands around its middle, something like the rings on a target or the stripes on a basketball. Tidy, proportional, modest. The reality is so far from that image that the word rings almost seems like the wrong word entirely. Saturn's ring system extends to an outer diameter of roughly 282,000 kilometers. That is 3/4 of the distance from Earth to our moon. If you remove the rings from Saturn and place them between Earth and the moon, they would fill most of that gap. The rings are not decorations. They are a world unto themselves, a flat disk of material spanning a distance that should take several days to drive across, if driving across empty space at highway speed were possible. And then comes the detail that makes even planetary scientists catch their breath when they first truly process it. Those rings, that vast hundreds of thousands of kilometers wide disk, are on average between 10 and 100 meters thick, not kilometers, meters. At their thinnest, the rings are no deeper than a 10-story building. If you took the main rings of Saturn and compressed them to the same proportions as a standard piece of paper, the paper would be more than 500 times thicker than the rings. You are picturing it now, a disk of ice and rock, 3/4 of the way to the moon, as thin as a parking structure, rotating, sparkling, essentially two-dimensional on a cosmic scale. The rings are enormous, and yet they are a whisper, a sheet of ice stretched across the sky. And there's something else about scale that tends to get lost in most descriptions of Saturn. Its moons. Saturn doesn't just have rings, it has a gravitational empire. 146 confirmed moons orbit Saturn. That's more than any other planet in the solar system. Not by a small margin, comfortably more than any other world. And those moons range from tiny tumbling rocks a few kilometers across to Titan, a world larger than the planet Mercury, with a dense atmosphere, lakes, rivers, rain, and seasons. Saturn's gravitational sphere of influence extends 54 million kilometers in every direction. For reference, the distance from Earth to the Sun is 150 million kilometers. Saturn's gravitational dominion is more than a third of the Earth-Sun distance. Any object that wanders within that zone is subject to Saturn's pull, potentially drawn into orbit or flung on a changed trajectory. Light, the fastest thing in the universe, takes between 1 and 2 hours to travel from Saturn to Earth, depending on where in our respective orbits we happen to be. When astronomers on Earth observe Saturn, they are seeing it as it was anywhere from 68 minutes to 84 minutes ago. They see its past, not its present. Every photograph ever taken of Saturn from Earth is a message from history. Recent history, yes, but history nonetheless. We have sent spacecraft to Saturn. The journey, even with the benefit of carefully calculated gravitational assists from Jupiter and other bodies, takes 7 years. 7 years of silent travel through the cold dark of the outer solar system, before the spacecraft arrives and catches its first close-up glimpse of the rings. When Cassini arrived in 2004, after traveling 3.5 billion kilometers, mission scientists described the first ring-crossing images as something they were not prepared for, even after years of anticipation. Because no simulation, no photograph, no briefing document can convey what it is like to see that system in detail. The rings resolve into thousands of individual bands, gaps, waves, and spirals. The surface of Saturn below reveals banded clouds, storms, and a disk so vast it fills a spacecraft camera from horizon to horizon. Scale has a way of asserting itself. Eventually, reality refuses to be imagined from a distance. But we are only beginning to understand what's really in those rings, because for all their obvious visual grandeur, for all the jaw-dropping numbers of width and span, the rings are hiding something. Something about their age, their physics, their future. Something that, when scientists finally pieced it together, made those beautiful bands of ice feel suddenly fragile. And fragile is exactly what they are. The rings that made Saturn famous. In the summer of 1610, Galileo Galilei made a sketch. It showed Saturn as three circles, a large central orb flanked by two smaller ones, pressed close on either side, almost touching the main planet. He was certain he was looking at companions, moons perhaps, or something else entirely. He described it in a letter to a patron as a planet with ears. Then in 1612, he looked again, and the ears were gone. Saturn had reverted to a single, unremarkable circle. Galileo was so unsettled that he joked bitterly that Saturn had devoured its companions like its mythological namesake devoured his children. He could not explain it. He couldn't. His telescope, revolutionary for its era, was simply not powerful enough to reveal the truth. The truth came 45 years later, in 1655, when a Dutch astronomer named Christian Huygens pointed a far superior instrument at the same planet. What he saw resolved into something unlike any previous astronomical observation, a flat disk floating freely around the planet, detached from it on all sides, inclined at an angle to our line of sight. Not moons, not ears, not companions. A ring, a continuous unbroken ring surrounding Saturn's equator, floating in space, touching nothing. In 1659, Huygens published his finding, and the scientific world quietly shifted on its axis. Saturn was unlike anything else in the known cosmos. It was and has remained the most visually arresting object in our solar system, the one planet that, when seen through even a modest telescope for the first time, consistently produces the same reaction, disbelief, a sense that the image cannot be real, that someone has placed a sticker over the eyepiece or played a trick. It looks fake because nothing in human experience prepares you for it. 15 years after Huygens, in 1675, Italian-French astronomer Giovanni Cassini was studying Saturn's ring when he noticed something. A gap, a dark band running around the ring, dividing it into an inner region and an outer region. He had discovered what we now call the Cassini division, a gap roughly 4,800 kilometers wide, sitting between what we now call the B ring and the ring. It appeared empty, dark, a void running through the middle of the most beautiful structure in the solar system. It was not actually empty, as later spacecraft would discover, but it was thin, sparse, kept clear by the gravitational resonance of Saturn's moon Mimas, which we will come to later. Cassini division, not a hole but a gravitational scar. For the next 3 centuries, astronomers would chart, classify, and categorize Saturn's rings from Earth, gradually resolving more detail as telescopes improved. They divided the rings into named sections: the D ring, the C ring, the B ring, the A ring, the F ring, the G ring, and the enormous, diffuse E ring far beyond the main system. Each ring has its own character. The B ring is the thickest and most opaque, so dense that when the Cassini spacecraft beamed radio signals through it, some frequencies were completely absorbed. You cannot see through the B ring. It is, in a sense, a solid wall of ice. Let's talk about what the rings are made of. The answer is, at first glance, almost anticlimactic. Water, not liquid water, but water ice. Frozen water, the same stuff you put in a drink, the same crystalline lattice that forms snowflakes. Between 90 and 95% of Saturn's ring material is water ice. The rest is rocky material and trace organic compounds. Frozen water, spread across hundreds of thousands of kilometers, catching the light of the distant sun and scattering it in every direction. Which is why the rings are bright, extraordinarily, almost shockingly bright, for something so far from the sun. Water ice is one of the most reflective substances in nature, and the rings are made of almost nothing else. When sunlight falls on them, they blaze back with a brilliance that has surprised astronomers since the dawn of the telescope era. The individual particles in the rings range from microscopic grains of frost to chunks of ice the size of houses. Most particles are in the centimeter-to-meter range, roughly the size of snowballs to boulders. They orbit Saturn at speeds of tens of thousands of kilometers per hour, separated from each other by distances ranging from centimeters to kilometers depending on the region. They are constantly, gently, endlessly colliding, nudging, clumping, grinding, and breaking apart in a perpetual slow-motion dance around the planet. From a distance, they look solid. From close up, from the perspective of a spacecraft threading through them, as Cassini did in its final months, they look like a snow globe. A vast, sparkling, slowly rotating snow globe, extending to the horizon in every direction. Here is the comparison that tends to land hardest. Take the main ring system, roughly 70,000 kilometers wide from the inner edge of the C ring to the outer edge of the ring. Now compare that width to the ring's average thickness, around 10 to 100 meters. Scale that to something touchable. If you took a sheet of standard printer paper and scaled it to the same width-to-thickness ratio as Saturn's rings, that paper would need to be more than 5 football fields wide, about 500 meters across. The rings, proportionally, are thinner than paper. They are an almost two-dimensional object projected across a three-dimensional space. That is what Saturn's most famous feature actually is. Not a band, not a disk, something closer to a veil. A film of ice stretched impossibly thin, impossibly wide, impossibly beautiful. But here is the question that hovered unanswered for centuries, and that scientists only began to resolve within the last few decades. Where did all this ice come from? What event created the rings? Why does Saturn, and essentially only Saturn among the planets of our solar system, possess such a dramatic ring system? The answer, when scientists finally arrived at it, when the data from Cassini was fully analyzed and the implications of the numbers were absorbed, was stunning. Not because it revealed something grand and ancient, but because it revealed something shockingly recent. And recent changes everything. The secret life of Saturn's rings. For most of human history, we assumed Saturn's rings were old, ancient, as old as the planet itself, 4.5 billion years of frozen history, orbiting quietly through the ages. It seemed obvious. The rings were so vast, so perfect, so integral to Saturn's identity, that of course they had always been there. Of course they were a primordial feature, born with the planet, destined to last as long as the solar system itself. We were wronged. The clue came from mass, specifically from the surprisingly small mass of the ring system, something that could only be measured properly when the Cassini spacecraft made its most audacious moves in the final year of its mission. During Cassini's grand finale, 22 daring orbits that sent the spacecraft threading between Saturn's cloud tops and the inner edge of the rings, scientists were able to measure the gravitational field of the rings directly. They could feel, through tiny changes in Cassini's trajectory, how much mass the rings contained, how much material was actually there. The answer was astonishing. The total mass of Saturn's main ring system is roughly equivalent to 40% of the mass of Saturn's moon Mimas, itself only about 400 kilometers across. All of those hundreds of thousands of kilometers of glittering ice, less than half the mass of a modestly sized moon. Far, far less material than anyone had expected, and less material means a younger age. Younger because the rings are constantly losing mass, losing it to a process that had been theorized for decades but wasn't fully confirmed until Cassini's final data was analyzed. Ring rained. It sounds almost gentle, but it isn't. Every second, somewhere between 10,000 and 100,000 kilograms of ring material, ice particles, are being pulled out of the rings by Saturn's magnetic field and drawn downward into the planet's upper atmosphere. Charged by ultraviolet radiation from the sun, tiny ring particles lose their ability to remain stably in orbit and begin spiraling inward. They enter Saturn's atmosphere and evaporate, adding water to the planet's clouds. Saturn is raining its own rings. At the rate Cassini measured, the entire main ring system would be gone in 100 to 300 million years, not billions of years, hundreds of millions. In cosmic timescales, that is not long. If the rings are losing mass this quickly, and if the ring system is as low mass as Cassini measured, then they cannot have been present for billions of years. The numbers don't work. Work backwards from the current mass and the current loss rate, and you arrive at an age of roughly 100 to 400 million years. When the Cretaceous period was drawing to a close on Earth, when T-Rex still walked, when the asteroid that would end the dinosaurs was still somewhere in space on its long, unknowing arc toward Earth, Saturn may have had no rings, or only a shadow of what exists today. So where did they come from? The most compelling hypothesis involves a moon, not a moon that exists today, but one that no longer does, a moon that wandered too close to Saturn at some point during the Cretaceous era of Earth's history, or perhaps slightly earlier, and paid the ultimate price. Every large body in the solar system has what is called a Roche limit, a critical distance from a massive body within which tidal forces overpower the object's self-gravity. Cross inside the Roche limit, and you begin to be torn apart. The same tidal forces that cause ocean tides on Earth, the difference in gravitational pull between the near side and far side of an object, become so extreme inside the Roche limit that they exceed the forces holding the object together. A moon that strays too close doesn't just get pulled in. It is stretched, stressed, cracked, and ultimately shredded into pieces. And those pieces, if they don't escape Saturn's gravity, settle into orbit around the equator. They spread out, they collide, they grind into smaller pieces, they become a ring. A moon died to give us Saturn's rings. We don't know its name because we never knew it existed. We have called it hypothetically chrysalis, a lost moon that broke apart and in breaking became the most beautiful structure in the solar system. A catastrophic death transformed into something magnificent. But the rings are not static monuments to that destruction. They are alive. The most mind-altering thing about Saturn's rings is that they are not simply sitting there. They are dynamic in ways that seem almost biological. They move, they wave, they knot, they braid, they form structures that shouldn't exist and persist in configurations that physics struggles to explain. Take the F ring, for example. Thin, narrow, and chaotic compared to the broad main rings, it sits just outside the ring, held in place by two shepherd moons, Prometheus and Pandora, orbiting just inside and outside it. Prometheus, the inner shepherd, is a small, potato-shaped moon only about 100 kilometers across. And every 15 hours, as it completes an orbit slightly faster than the F-ring material, it passes close enough to the ring to pull on it gravitationally, drawing out streamers of ice, creating dark channels, and then, as it moves away, distorting those channels into kinks and braids. The F-ring looks like someone knotted it, because something did. Every orbit, Prometheus reaches in like a hand through a curtain, grabs a handful of ring material, pulls it out of place, and then releases it. Over time, the ring develops a complex, twisted structure, a braided appearance that Voyager images first revealed in 1980, and that mystified astronomers for years before the physics was worked out. Then there are the spokes. When Voyager flew past Saturn, it captured something in the rings that nobody expected: dark, radial features stretching like wheel spokes across the face of the B-ring, not following the ring material's orbital direction, but projecting outward from the planet's center, as if drawn by a compass. They appeared and disappeared over hours. They rotated, not with the ring particles, but with Saturn's magnetic field. They were something between a shadow and a substance, dark against the ring's bright background. Nobody fully understood them. Even Cassini, when it arrived decades later and observed the spokes again, provided data that constrained the explanations but didn't definitively confirm one. They are likely caused by charged dust particles levitated above the ring plane by electromagnetic forces, tiny motes of dust hovering, organized by the planet's magnetic field into radial streaks. But the complete story of the spokes, why they appear seasonally, why they are confined to the B-ring, what determines their intensity, remains an open scientific question. And then there is the Cassini grand finale itself, 22 orbits between the ring and the planet, a region that engineers had been uncertain about whether Cassini could survive, ring particles raining into the spacecraft at orbital velocities. The possibility of damage, of systems being knocked offline, of the mission ending prematurely. Instead, the spacecraft survived all 22 orbits, and the data it returned from that gap between the rings and the planet has reshaped our understanding of the ring system more than any other single dataset. What scientists found in that gap was not emptiness. It was a complex plasma environment, charged particles and electromagnetic fields, ring rain falling into Saturn's atmosphere, waves and oscillations propagating through the ring system and into the planet below. The gap between Saturn and its rings was a dynamic, connected, interactive zone, not a void, but a bridge. In its final orbit, Orbit 23, Cassini turned its antenna toward Earth one last time, transmitting data at the highest possible rate, squeezing out every last bit of information. Then it crossed the ring plane for the last time, entered Saturn's upper atmosphere, and was destroyed. Not violently, gradually, like a meteor, heating and ablating as the atmospheric pressure built around it. The spacecraft that had revolutionized our understanding of Saturn becoming part of Saturn, returning, in a sense, to the world it had spent 13 years studying. What Cassini discovered in those final plunges, the ring mass, the ring rain, the gap environment, gave scientists the final pieces needed to confirm what the numbers had been suggesting for years. The rings are young, the rings are dying, and we, humanity, are living through a unique window in the solar system's history, the brief, cosmically improbable era during which Saturn's rings exist in their full, glorious form. In 100 million years, or perhaps 300 million, or perhaps somewhere in between, the rings will be gone. Saturn will still be there, still enormous, still commanding, still spinning too fast, still floating on hypothetical water. But the rings will be gone, just Saturn, its moons, and the memory of ice. But before we look that far ahead, let's look inward, into Saturn itself. Because beneath those rings, beneath those bands of cloud visible in every photograph, something is happening that makes even the ring dynamics look tame. Storms, not like any storm on Earth, not like any storm anywhere in the solar system except perhaps Jupiter. Storms so large, so violent, and so long-lived that they challenge our understanding of weather itself. Saturn is not as peaceful as it looks. The storm's larger than Earth. There is a fantasy that the outer solar system is calm, that beyond the asteroid belt, beyond the rocky turmoil of the inner planets, space settles into a kind of serene stillness, cold, yes, dark, yes, but peaceful, that the gas giants hang in their orbits like enormous placid ornaments, beautiful from a distance, quiet. That fantasy does not survive contact with Saturn's atmosphere. Saturn is a world of almost incomprehensible violence. Not the sudden, explosive violence of a volcanic eruption or an earthquake, but something slower, more sustained, and in some ways more terrifying. A violence woven into the planet's very structure. A violence that has been running continuously for longer than complex life has existed on Earth. Start with the wind. At Saturn's equator, the jet stream blows at approximately 1,800 kilometers per hour. Let that number find its scale. Earth's most powerful hurricanes sustain winds of perhaps 300 kilometers per hour. The strongest tornado ever recorded topped out around 480. Saturn's equatorial jet stream is 6 times faster than the most violent storm ever measured on Earth, and it is not a storm. It is not exceptional weather. It is Saturn's baseline, its normal, its average Tuesday. That wind blows continuously, without interruption, without seasonal weakening, without landfall to sap its energy. Because there is no land. On Earth, storms die when they hit coastlines. They convert their oceanic fuel into destruction and then dissipate over terrain. On Saturn, there is no terrain, there is no coast. There is no place where the atmosphere ends and something solid begins. The gas simply thickens, gradually, with depth, becoming denser and hotter, but never solid, never stopping. The storms that form on Saturn have nowhere to go. They persist, intensify, wander, and occasionally merge into something so large it becomes visible from Earth. These planet-scale eruptions are called Great White Spots, and they appear on Saturn roughly every 30 years, approximately once per Saturnian year. They are not subtle, they are not background features. They are emergent catastrophes, rising from deep within Saturn's atmosphere and expanding across the face of the planet, until they can be seen through a decent backyard telescope from 1.5 billion kilometers away. The most recent Great White Spot erupted in December 2010, and Cassini had a front row seat. It began as a bright white smudge in Saturn's northern hemisphere, a convective thunderstorm rising from the deep troposphere, where temperatures and pressures are extreme enough to cause water to condense and release enormous quantities of latent heat. That heat drove the storm upward, punching through the atmospheric layers like a fist through thin fabric. Within weeks, the storm had expanded. Within months, it had encircled the entire planet, a band of churning white cloud 300,000 kilometers long, wrapping completely around Saturn's northern hemisphere. A storm so large that if you laid it end to end, it would stretch most of the distance from Earth to the Moon. The storm produced lightning, not the gentle, momentary discharges of an Earth thunderstorm, but sustained, repeated bursts of electromagnetic energy so powerful that Cassini's instruments detected them from orbit. Saturn's lightning is roughly 10,000 times more energetic than Earth's. Each discharge releases energy comparable to a small nuclear weapon, and during the 2010 storm, they were occurring constantly, hundreds of times per hour, for months. The storm eventually wrapped around the planet so completely that its leading and trailing edges began to collide with each other. The front of the storm ran into its own tail. What happened next was something scientists had never observed before. The two parts of the storm began destroying each other. The interaction created a massive anticyclonic vortex, a dark, stable oval that persisted long after the white cloud bands had dissipated, a scar left by a storm consuming itself. But where does all this energy come from? What powers Saturn's weather at a level that dwarfs anything in the inner solar system? Part of the answer is that Saturn is not purely dependent on the Sun. Saturn generates its own heat, producing roughly 2.5 times more energy than it receives from our star. From 1.5 billion kilometers away, the Sun's energy is already weak. At Earth's distance, sunlight can warm skin and drive weather. At Saturn's distance, sunlight is roughly 100 times dimmer, insufficient by itself to power the extreme atmospheric dynamics we observe. So Saturn supplements it from within. This internal heat source is not nuclear fusion. Saturn is not a failed star, not large enough to ignite hydrogen in its core. Instead, the heat comes from something more subtle, more alien, and frankly more poetic. Helium is reigning. Inside Saturn, deep below the visible cloud layers, temperature and pressure conditions are extreme enough that something extraordinary happens. Helium, which makes up roughly a quarter of Saturn's mass, condenses into droplets, not raindrops as we know them, but spherical collections of liquid helium forming within the metallic hydrogen layer of Saturn's deep interior. These droplets are denser than the surrounding hydrogen, and so they fall, slowly, relative to human timescales, but continuously. Droplets of liquid helium drifting deeper and deeper into Saturn's interior, converting gravitational potential energy into thermal energy as they descend. Helium rain, falling through a metallic hydrogen sea, warming the planet from the inside out. This process, helium rain, is one of the most exotic naturally occurring phenomena in the entire solar system. It cannot happen on Earth. The conditions required, temperatures of thousands of degrees, pressures millions of times greater than Earth's surface, don't exist naturally anywhere on our planet. You would need to build a machine to recreate the conditions. Saturn has been running that machine for 4 billion years. And the helium rain does something else. As helium falls out of the upper layers and sinks deeper, the upper atmosphere becomes helium depleted, which is exactly what measurements of Saturn's atmosphere show. Saturn's upper atmosphere has less helium than it should, given the solar system's original composition. The missing helium isn't gone, it's deeper, raining down, warming the planet, powering the storms, driving the winds. But here's where it gets strange again, because beneath the visible cloud layers, beneath the gas phase of Saturn's atmosphere, pressure builds to a point where something happens to hydrogen that has no everyday analog on Earth. Hydrogen, normally the simplest, lightest gas, is compressed so extremely that its electrons become delocalized. They stop belonging to individual atoms. They flow freely through the compressed hydrogen in the same way electrons flow through copper wire. The hydrogen becomes electrically conductive. It becomes liquid metallic hydrogen, a state of matter that doesn't occur naturally anywhere on the surface of our planet, a state that was only theoretically predicted in 1935 and only experimentally confirmed in laboratories in 1996. Saturn contains a vast ocean of this material, an ocean of liquid metal that conducts electricity, flows like a fluid, and is threaded through with the planet's magnetic field. This ocean is probably what generates Saturn's magnetic field, the circulation of metallic hydrogen acting as the dynamo. But as we mentioned earlier, that magnetic field is almost perfectly aligned with Saturn's rotation axis, which shouldn't be possible for a dynamo. The helium rain may offer a partial explanation. As helium droplets fall through the metallic hydrogen layer, they scatter and deflect the electrical currents that generate the magnetic field. The helium rain may be smoothing out the asymmetries, hiding the underlying chaos of the dynamo beneath a veneer of almost perfect alignment, polishing the magnetic field like a stone in a river. Almost, the mystery is not fully solved, not yet. But something else is happening at Saturn's poles that makes the atmospheric dynamics look straightforward by comparison. Something that, when Voyager first photographed it in 1980, scientists simply did not believe. A hexagon. The hexagon nobody can fully explain. Nature has rules, implicit deep mathematical rules that govern the shapes of things. Coastlines are irregular, mountains are jagged, clouds are billowing and formless, planets are round. These are not arbitrary preferences, they are the consequences of physical processes playing out over time. The chaotic turbulence of fluid dynamics, the smoothing influence of gravity, the fractal patterns of erosion and deposition. Geometry in the formal sense, regular polygons, perfect angles, sharp mathematical corners, is not generally nature's style, unless you build it deliberately, unless you are an engineer or an architect, unless you have a plan. And yet, sitting at Saturn's North Pole, rotating steadily, persisting across decades, spanning a distance wide enough to swallow two Earths side by side, is a perfect hexagon. Not approximately hexagonal, not hexagonal in the same vague way that a stop sign is hexagonal. A genuine six-sided geometric figure, with sides of roughly equal length, six corners that are actually corners, a persistent internal structure, and most inexplicably extraordinary stability. Voyager 1 photographed it in 1980. Voyager 2 confirmed it in 1981. Cassini photographed it starting in 2004, more than 2 decades later. It was still there, still rotating, still hexagonal. The same structure, the same shape, holding itself together across the lifetimes of spacecraft, across decades of Saturn's brutal atmospheric dynamics. Nothing in any planet's atmosphere should do this. Let's put the numbers in context. Each side of Saturn's hexagon is approximately 13,800 kilometers long. By comparison, Earth's diameter is 12,742 kilometers. Each side of the hexagon is longer than our entire planet is wide. The total span of the hexagon, corner to corner across its width, is about 30,000 kilometers. Inside the hexagon, there is enough room to comfortably fit two Earths side by side. And it is a jet stream, a polar jet stream, a band of high-speed winds circling Saturn's North Pole that has somehow organized itself into a hexagonal path rather than the simple, roughly circular path that polar vortices take on every other planet we know of, including Earth, which has its own polar vortex, which is circular, as you would expect. Saturn's polar jet doesn't curve smoothly back on itself. It makes 6 turns, 6 distinct angular changes of direction, each roughly 60 degrees before completing its loop and meeting itself where it started. The winds inside the hexagon reach approximately 320 kilometers per hour. The boundary of the hexagon is a sharp shear line. Inside the hexagon, the atmosphere rotates one way. Outside it, the atmosphere rotates differently. The hexagon is a wall of wind. When scientists first saw it, the reaction was not immediate understanding. It was confusion, and then, gradually, curiosity. What could possibly cause a gas giant's atmosphere, a fluid, turbulent, chaotic medium, to lock itself into a 6-sided polygon? The laboratory held part of the answer. Researchers at Oxford University conducted a famous series of experiments in which they placed a rotating tank of water on a turntable, and then introduced a smaller rotating cylinder of water inside it, spinning at a different speed. The two bodies of water, rotating at different rates in the same container, developed an interference pattern between them. Wave interference. The inner rotating body created waves that propagated outward and interacted with the outer rotating flow, and depending on the speed ratio between the two, the interference pattern locked into a polygon, a triangle, a square, a pentagon, a hexagon. The number of sides depended on the ratio of rotation speeds. 6 sides appeared at a specific ratio, and that ratio, when compared to Saturn's atmospheric rotation rates, the difference in speed between the polar jet stream and the surrounding atmospheric layers produced the conditions for hexagonal resonance. In other words, the hexagon is a standing wave, a resonance pattern frozen into Saturn's atmosphere by the interaction of different flow speeds at different latitudes. Like a guitar string vibrating in a specific mode, Saturn's atmosphere is oscillating in the 6th mode, and that oscillation has been stable for at least 40 years of direct observation, and almost certainly far longer. But the standing wave explanation, while compelling, doesn't explain everything. it doesn't fully account for why the hexagon rotates at essentially the same speed as Saturn's internal radio emissions, suggesting it is somehow connected not just to the upper atmosphere but to something deeper, to the planet's interior, to the magnetic field, to the same deep processes that drive the storms and the helium rain. The hexagon may be a surface expression of something much deeper, a resonance not just in the atmosphere, but extending down through the layers, all the way to the region of liquid metallic hydrogen below, a standing wave that reaches from the clouds to the core. And in 2018, Cassini data revealed something that made the hexagon even stranger. It had a companion, a secondary hexagonal structure in Saturn's upper stratosphere, far above the main hexagon, matching its size and rotating in the same direction. A second hexagon, like a shadow of the first one, floating above it in the sky. The upper hexagon formed in the same way an analog forms on Earth, when Saturn tilted its northern hemisphere toward the Sun and began receiving more sunlight. The heating created a vortex in the stratosphere that, interacting with the lower hexagon's geometry, adopted the same six-sided shape. A hexagon reflected in the sky above a hexagon, as if Saturn decided that one geometrically impossible atmospheric structure wasn't enough. Inside the main hexagon, at its very center, sits something else. A storm, a hurricane, technically, with an eye visible from space, not a small eye, an eye approximately 50 times larger than the average hurricane eye on Earth. Surrounded by towering walls of cloud, rotating with the calm certainty of something that has no intention of dissipating anytime soon. The calm at the center of the hexagon is not really calm. It is the eye of something ancient and unceasing, surrounded on all sides by the most geometrically improbable boundary in the solar system. And the hexagon changes color. Over the 7-year progression of Saturn's seasons, its northern hemisphere tilting gradually toward and then away from the Sun, the hexagon changes hue. In Cassini's early images, photographed during Saturn's northern winter when the pole was in shadow, the hexagon appeared blue. As sunlight returned, it shifted through blue-green, through gold, through amber. By the time Cassini's mission ended in 2017, the hexagon had turned a golden yellow-brown. Driven by photochemical reactions in the atmosphere, sunlight breaking down organic molecules, and creating the same haze compounds found throughout Saturn's atmosphere, the entire polar structure cycled through colors like a slow planetary mood ring. Blue to gold, winter to summer, across a 7-year planetary season, on a world 1.5 billion kilometers from the Sun. Nothing else like it exists anywhere in the known solar system. Not on Jupiter, not on any of the ice giants, not on any exoplanet we have been able to resolve in detail. The hexagon is Saturn's alone, a mystery that is partially understood, partially explained, and still, in its deepest aspects, not fully accounted for. What creates the hexagon below the clouds in the fluid metal interior? Why is it so stable, and for how long has it been there? Could it have existed for billions of years, since Saturn's early history? Or does it form and dissolve on timescales we haven't been watching long enough to see? We don't know, not yet, but the hexagon is not the last surprise Saturn has hidden at its poles. Because surrounding the planet, extending millions of kilometers into space, is a region so hostile, so saturated with lethal radiation and charged particles, that it makes the surface of Saturn's moons feel almost welcoming by comparison. The space around Saturn is beautiful, and it will kill you. The most dangerous place around Saturn. Stand anywhere on the surface of our moon and look up. The sky is black, stars are visible, and the radiation environment, without Earth's protective magnetosphere, would expose you to a dose of high-energy particles, solar wind, and cosmic rays that would be dangerous over the course of days and fatal over weeks. The moon is, by any measure, a hostile environment for unshielded biology. Now move to Saturn. Saturn's magnetosphere, the vast bubble of magnetic influence surrounding the planet, extends approximately 1 to 2 million kilometers on the side facing the Sun, and trails off for tens of millions of kilometers in the direction away from the Sun, stretched into a long magnetotail by the pressure of the solar wind. Inside this magnetosphere, charged particles, protons and electrons, are trapped and accelerated by the magnetic field lines. They race around the planet, bouncing between the magnetic poles, accumulating energy, densifying in certain zones into something analogous to Earth's Van Allen radiation belts. But Saturn's radiation environment is not analogous to Earth's. It is substantially more intense. A human placed in Saturn's inner radiation zone, without shielding, would receive a lethal radiation dose within minutes, not hours, minutes. The charged particles in those belts are energetic enough to penetrate skin, damage DNA, destroy biological tissue, disrupt electronics. Even Cassini, a spacecraft designed for the radiation environment of the outer solar system, carried shielded electronics specifically because of what Saturn's radiation belts would do to unprotected systems. And yet Saturn's magnetosphere is also, in a strange way, partly cleaned, partly suppressed, by the very ring system we spent 2 chapters admiring. As Saturn's rings sweep through the inner radiation belt, ring particles absorb charged particles from the belt. Each grain of ice, each boulder of frozen water, sweeps up electrons and protons from the surrounding space as it orbits. The rings act as a sponge, not a perfect sponge, not even a particularly efficient one across their full extent, but enough to create a detectable gap in the inner radiation belt. The most intensely dangerous zone, just inside the inner edge of the rings, is partially cleared by this absorption. The rings create a shadow in the radiation field. This is not metaphorical, it is literal. You can map the inner radiation belt and see the imprint of the rings upon it. But the radiation belts are only one component of Saturn's complex electromagnetic environment. The magnetosphere itself is doing something unusual, something that, like so many things about Saturn, turns out to violate what we thought we knew. Here is the rule: every planet that generates a magnetic field does so through what is called the dynamo effect, the movement of electrically conductive fluid in the planet's interior, driven by heat and rotation, generating and sustaining a magnetic field. Earth's dynamo runs on liquid iron in the outer core. Jupiter's runs on metallic hydrogen in the deep interior. Saturn's presumably runs on its own metallic hydrogen ocean. And the fundamental requirement of a dynamo is asymmetry. The conducting fluid must circulate in patterns that are not perfectly symmetric around the rotation axis. Without asymmetry, the currents cancel each other out. The field collapses. You need the magnetic poles to be offset from the geographic poles, offset by some angle, even a small one. Earth's magnetic and geographic poles are currently offset by about 11 degrees, Jupiter's by about 10 degrees. Almost every planet with a magnetic field has this offset. Saturn's offset, less than 1/100th of a degree, essentially zero. Dynamo theory says this cannot sustain a magnetic field. The symmetry should cause the field to collapse. And yet there is the field, strong enough to trap radiation particles, strong enough for Cassini to measure precisely for 13 years, stable enough to persist across however long Saturn has been a planet. We mentioned in the storms chapter that the helium rain may partly explain this, by smoothing out the asymmetries in the metallic hydrogen layer, creating an apparent alignment, while the actual dynamo asymmetry persists deeper inside. But partly explain is honest science's way of saying, we don't fully understand it yet. The magnetic field alignment of Saturn remains one of the most intriguing unsolved problems in planetary physics. And into this already complicated electromagnetic environment, Saturn's moons are injecting material. We'll talk extensively about Enceladus in later chapters, but for now, consider this. Enceladus, that small and apparently frozen world, is shooting water vapor into space from its south pole at 1,400 kilometers per hour. That water vapor, those icy particles, are being captured by Saturn's magnetosphere. They orbit Saturn in a broad torus, a donut-shaped ring of plasma centered on Enceladus' orbit. This plasma torus feeds material directly into the magnetosphere. Enceladus is not just an orbiting moon. It is an active contributor to Saturn's electromagnetic environment. It is changing the space around Saturn, influencing the radiation belts, altering the plasma density, affecting the way Saturn's magnetic field interacts with the solar wind. A moon so small it could fit within the UK is reshaping the magnetic environment of the second largest planet in the solar system. Saturn also has auroras. They are not visible to the naked eye, and they don't dance in the colors of Earth's northern lights. They emit primarily in ultraviolet and infrared wavelengths, detectable only by instruments. But they are there, swirling at both poles, driven by the same interaction between solar wind and magnetic field that creates auroras on Earth. Saturn's polar auroras are extraordinary in scale, broader, more complex, influenced not just by the solar wind, but by the plasma torus fed by Enceladus and other moons. When Cassini turned its ultraviolet spectrograph toward Saturn's poles, it captured curtains of light stretching thousands of kilometers into space. A light show with no audience, repeated continuously, on a world 1.5 billion kilometers from Earth. There is something else that Cassini recorded in Saturn's magnetosphere, something that had been detected first by Voyager and that defied easy explanation for decades. Saturn produces radio emissions, bursts of electromagnetic radiation in the kilometer wavelength range, called Saturn kilometric radiation. This radiation was initially used to try to determine the length of Saturn's day, since it was assumed to rotate with the planet's interior. But the emissions turned out to be more complex, varying in frequency and intensity in ways that seemed to shift over years, almost as if Saturn's magnetic field were slowly processing or breathing. The radio emissions of Saturn, converted to audio frequencies, produce a sound unlike anything on Earth. Not the roar of thunder, not the hiss of static, something stranger, more melodic, shifting and cycling with an alien rhythm. Cassini recorded these sounds, and NASA released the recordings. If you have never heard them, look them up. They are haunting. They are the voice of a planet, electromagnetic emissions from a magnetic giant, translated into something our ears can register. It is Saturn, speaking in a language we are only beginning to learn to interpret. But the most consequential thing about Saturn's magnetosphere, the thing that makes it most scientifically significant right now, is what it tells us about Enceladus. Because the material Enceladus is injecting into Saturn's space is not just water. It contains something far more interesting, far more suggestive, far more important. And the story of that material, and what it implies about that tiny, frozen, geyser-covered moon, is one of the most extraordinary stories in all of planetary science. To tell it properly, we need to start somewhere unexpected. We need to start on Earth, at the bottom of an ocean in total darkness, around a hydrothermal vent that nobody knew existed until 1977, and that changed our understanding of where life can survive. And then we need to travel 1.5 billion kilometers to a moon that may be doing the same thing, right now, in an ocean nobody has ever seen. But first, before we get to the moons, we need to understand where we're going. We need to understand what Titan is, because Titan is not a moon, not really. Not in the way most moons are moons. Titan is a world, and it is one of the strangest, most familiar, most hauntingly alien worlds we have ever encountered. Titan and alien Earths. Close your eyes for a moment. Picture Earth, not the Earth of cities and roads and satellites, the Earth of 4 billion years ago, the Earth before multicellular life, before complex organisms, before photosynthesis had begun to flood the atmosphere with oxygen. The early Earth when the sky was orange-brown with a thick haze of organic compounds, when the oceans were young and warm, when simple chemistry was slowly, tentatively, groping toward biology. Now freeze that Earth, drop it to minus 179 degrees Celsius, replace the water with liquid methane, move it 1.5 billion kilometers from the Sun, put it in orbit around Saturn. Open your eyes, you are looking at Titan. Titan is Saturn's largest moon. It is, by almost any measure, an extraordinary world. It is larger than the planet Mercury, 5,149 kilometers across, compared to Mercury's 4,879. If Titan orbited the Sun directly rather than Saturn, we would call it a planet without hesitation. It is a world complete in itself, layered, complex, active, and in some of its most important characteristics, breathtakingly Earth-like. It is also completely, profoundly alien. Let's start with the atmosphere. Titan is the only moon in the solar system with a dense atmosphere, not a thin wisp of gas clinging to its surface, not a trace of volatiles leaking into space, a genuine, substantial, persistent atmosphere. At Titan's surface, the atmospheric pressure is about 1.5 times Earth's sea level pressure. You would feel it. You would feel the air pushing against you from every direction, slightly more than here on Earth. The air would be dense enough to require no pressure suit. You could walk the surface of Titan without a spacesuit protecting you from the pressure. You would need an oxygen mask and a very good thermal suit, but the pressure would be fine. The atmosphere is 98% nitrogen, the same gas that makes up 78% of Earth's air. Nitrogen, colorless, inert, the filler gas of terrestrial atmospheres. On Titan, it completely dominates, with methane making up most of the remainder, and trace amounts of hydrogen, ethane, acetylene, and dozens of complex organic molecules completing the mixture. Those organic molecules, synthesized in Titan's upper atmosphere when sunlight and energetic particles break apart nitrogen and methane molecules and encourage them to recombine in new configurations, fall slowly through the atmosphere as a fine orange-brown haze. Tholins, scientists call them. Complex prebiotic organic molecules, not yet alive, not yet assembled into anything that can reproduce or metabolize, but chemically sophisticated in ways that hint at life's ingredients. Titan is raining organic chemistry onto its own surface, continuously, for billions of years. The surface is invisible from space. No optical telescope or camera can see through the haze. It took the Cassini spacecraft's radar, which can penetrate the atmosphere and map the surface below by bouncing radar pulses off the terrain, to reveal what Titan actually looks like. And what it revealed was something extraordinary. Rivers, not metaphorical channels that might once have been rivers, but features shaped like rivers, branching tributaries merging into larger channels, carving their way through the landscape, flowing toward lower ground. Shorelines, the characteristic concave curves of a coastline meeting a body of liquid. Deltas where channels empty into broader flat areas. The unmistakable geography of a world shaped by flowing liquid. And then in the polar regions, lakes. Dark, flat, radar-absorbing features that could only be one thing: bodies of liquid sitting on Titan's surface. Not ancient dried lake beds, not geological remnants. Current, present, contemporary lakes. Active, real here, today, and presumably here, tomorrow lakes. But not water. The temperature is minus 179 degrees C. Water is solid at that temperature. The liquid on Titan's surface is methane natural gas, the stuff that comes out of your kitchen stove, liquefied by Titan's extreme cold into a substance that laps at the shores of alien coastlines and evaporates into an orange sky to form clouds and fall as rain. The methane cycle on Titan mirrors the water cycle on Earth with an almost uncanny precision. Methane evaporates from the surface. It rises into the atmosphere where it condenses into clouds. It falls as rain, large, slow-moving drops in Titan's thick air and lower gravity. It runs off the surface in rivers, collects in lakes and seas, and sits there, evaporating again, continuing the cycle. A complete closed hydrological cycle, except instead of water, it runs on natural gas. We know all of this because, in 2005, we went there. The Huygens probe, built by the European Space Agency, carried to Saturn by NASA's Cassini spacecraft, was released from Cassini in December 2004. It coasted through space for 3 weeks. Then, on January 14, 2005, it hit Titan's atmosphere at nearly 6 kilometers per second and began its descent. For the next 2 hours and 27 minutes, Huygens fell through Titan's atmosphere, slowed by a parachute, instruments recording everything: temperature, pressure, wind speed, chemical composition, a comprehensive portrait of an alien sky, transmitted back through Cassini to Earth. And as it descended, it photographed, frame after frame, building a panorama of the surface below. Rivers, channels, rounded stones, not rock but water ice, smoothed by flowing methane, scattered across the surface near the landing site like a rocky beach at low tide. Then Huygens landed, soft landing. It touched down on material described as damp, slightly compressible, something with the consistency of wet sand or lightly packed snow. It sat there on the surface of Titan and continued transmitting for 72 minutes before its battery died and it fell silent forever. During those 72 minutes, Huygens was the most distant soft-landed object ever placed by humanity. It sat on the surface of a moon, 1.2 billion kilometers from Earth at the time of landing, surrounded by water ice pebbles rounded by methane rivers, under an orange sky it could not see through. What scientists noticed, listening to the audio recordings made during descent, was not dramatic. It was quiet. Not silent, there were sounds, the hiss of wind, the distant crackle of atmospheric turbulence, but mostly quiet. The thick air muffled everything. Sound travels differently in Titan's dense nitrogen-methane atmosphere, slower than on Earth, with different frequency characteristics. The experience of listening to Huygens' descent audio is eerie, almost familiar, like listening through a thick wall to weather outside, the suggestion of an active world, muted by distance and density. And that sense of almost familiarity is perhaps the strangest thing about Titan. It feels like somewhere we know. Geology shaped by liquid cycles, river valleys, lake shores, weather, seasons, and active atmosphere, all the hallmarks of a world we'd recognize. But offset, translated into a different chemistry, a different temperature regime, a different solar light level. Earth seen through a glass darkly, or Earth seen from a different universe, one where the rules are the same but the materials have been swapped. Titan's dunes are another expression of this uncanny familiarity. Cassini's radar revealed vast fields of linear dunes in Titan's equatorial region, not sand dunes, but hydrocarbon dunes. Particles of organic material, the size of sand grains, driven by Titan's winds into the same long, parallel ridges you'd find in the Sahara or the Arabian Desert. Some of these dunes are over 100 meters tall and stretch for hundreds of kilometers. An alien desert, shaped by alien wind, built from alien particles, following exactly the same physics as any desert dune on Earth. Titan has seasons. Long ones, Saturn takes 29.5 years to orbit the Sun, so each Saturnian season lasts about 7.5 Earth years. Cassini observed Titan across nearly a full Saturnian year and documented the atmospheric changes that came with the seasons. Cloud formations migrating between hemispheres, lake levels changing, storm systems developing in the summer hemisphere. A world with a rhythm, a cycle, a year. And Titan, unlike Enceladus, which we'll meet properly in the next chapter, hides its secrets well. Its haze prevents visual observation of the surface. Its extreme cold makes any life based on water impossible at the surface. Its chemistry is rich but alien. And yet scientists keep coming back to Titan, keep designing missions to Titan, keep arguing about Titan, because somewhere beneath all that orange haze and below those methane seas and beneath that surface of water ice, something might be happening. Something that has been happening, quietly and slowly and persistently, for billions of years. The methane on Titan is being destroyed. Ultraviolet radiation from the sun breaks methane molecules apart. Over time, methane should be depleted, and yet there it is, still present, still cycling, still raining. The atmosphere should have lost its methane long ago. Something is replenishing it. Something is putting methane back. What is that something? One possibility is geological subsurface reservoirs of methane, volcanic processes releasing it slowly, cryovolcanism replenishing the atmospheric supply. Plausible, reasonable, safe. Another possibility, not proven, not confirmed, not yet demonstrated, is that something on Titan's surface is producing methane as a metabolic byproduct, that the methane cycle is not purely geological, that it is, at least partly, biological. We have not ruled this out. The lakes of liquid methane. There is a sea on Titan. Not a lake, not a pond, a sea. It is called Kraken Mare. The name comes from the legendary North Sea monster, vast, dark, tentacled, rising from the depths of an ocean that sailors feared to cross. The astronomers who named it were not being whimsical, they were being accurate. Kraken Mare, as mapped by Cassini's radar, covers an area of approximately 400,000 square kilometers. For comparison, the Caspian Sea, the largest lake on Earth, covers 371,000 square kilometers. Kraken Mare is larger. It is not a feature of Titan. It is a dominant geographical feature, a dark, liquid sea filling Titan's North Polar region, edged by shorelines, fed by rivers, lapping at the bases of ice cliffs that rise from its margins. It is made of liquid methane and ethane, the same hydrocarbons that fuel our civilization, liquefied by temperatures that would freeze a human solid within seconds, sitting on the surface of a moon of Saturn, 1.5 billion kilometers from Earth, a sea of natural gas, large enough to swallow a European country under an orange sky. Kraken Mare is not alone. Two other large seas sit in Titan's polar region, Ligeia Mare, at roughly 126,000 square kilometers, and Punga Mare, smaller still. And surrounding these seas, filling the polar regions to their margins, are hundreds of smaller lakes, some large, some small, some isolated, some connected to the seas by narrow channels. Titan's polar regions look, in Cassini's radar maps, like a complex coastal geography, an Arctic landscape of fjords and islands and broad estuaries. Except the liquid is methane, the bedrock is water ice, and the sky is orange. The methane lakes exist because Titan is cold enough, just barely, for methane to remain liquid at the surface. Methane's boiling point at Earth-like pressures is -161 degrees C. At Titan's surface pressure, slightly higher, the boiling point shifts, and Titan's surface temperature of -179 degrees C sits just below that threshold. Methane at the surface is close to its boiling point. It exists as liquid, but only barely. A few degrees warmer and it would evaporate. The lakes of Titan are, in a sense, at the edge of their own existence. Scientists have been able to estimate the depth of some of these bodies using Cassini's radar, and in the case of Ligeia Mare, one of the best studied, the depth reaches at least 160 meters in some places, and possibly more. This is significant, not just as a number, but as an implication. A sea 160 meters deep, filled with liquid methane and ethane, has had time to accumulate, to deepen, to develop layering, the heavier ethane sinking to the bottom, lighter methane remaining near the surface. Cassini's data suggested this compositional stratification might actually exist, a two-layer sea, methane on top, ethane below. Waves should exist on Titan seas. In principle, wind blows across the surface, it stresses the liquid, and waves form. But early Cassini radar passes showed the surface of Ligeia Mare and Kraken Mare as almost perfectly flat, mirror-smooth, with no detectable roughness. This puzzled scientists. Why no waves? The answer involves Titan's particular physics. The Moon's lower gravity, only 14% of Earth's surface gravity, means that wave-driving forces are weaker. The higher viscosity of the methane-ethane mix means the liquid resists deforming. And winds at Titan's surface are generally calm, only a few meters per second, because Titan's thick atmosphere and distant sun drive only gentle atmospheric circulation. The result is seas of extraordinary stillness, flat, dark, mirror surfaces that reflect the orange sky above with perfect clarity. Some later Cassini passes did detect potential wave features, small roughness signatures in the radar return that could indicate very low waves, perhaps centimeters tall. Titan seas may have subtle waves, but they are nothing like the churning ocean surfaces we know on Earth. Standing at the shore of Kraken Mare, you might be looking at something closer to a perfectly calm lake on a windless day, the liquid barely moving, the horizon flat and dark, the sky overhead a dim, orange glow. But some of Titan's lakes are more mysterious than the great seas. Scattered across the polar regions are smaller lakes, sitting in what appear to be flat-floored depressions without obvious drainage channels. They don't have rivers flowing into them. They don't appear to be connected to the main seas by surface channels. They just sit there, isolated pools of liquid methane in the landscape, as if they appeared from nowhere. One hypothesis is that these lakes fill from below. That subsurface methane, stored in porous water ice bedrock, wells up through cracks and seeps, filling the depressions from underneath. Methane springs, feeding surface lakes from below. This would mean Titan has active subsurface hydrology, a methane groundwater system operating beneath the surface, replenishing surface lakes without visible rivers. And then there are Titan's most baffling lake features, the Magic Islands. These are transient radar-bright features that appeared in some Cassini passes and disappeared in others. In one image of Ligeia Mare, a bright feature, roughly 260 square kilometers in area, appeared near the southern shore. In a later pass, it was gone. In another pass, something similar appeared in a different location. These features come and go. They are not permanent. They are not fixed geography. What are they? The leading candidates include floating hydrocarbon solids, chunks of waxy organic material buoyed to the surface, carried by currents and then sinking again. Or nitrogen bubbles, released from solution in the lake as temperatures change slightly, rising to the surface and creating a froth of nitrogen gas before dissipating. Or perhaps waves, genuine surface waves, large enough to catch the radar in certain geometries but not in others. None of these explanations is fully confirmed. The Magic Islands remain unexplained. Titan, as a habit, generates mysteries at the rate it generates methane rain. And speaking of methane, let's return to the problem of its replenishment. The atmosphere of Titan contains enough methane to sustain its current cycle for perhaps 10 million to a billion years, depending on the model. But the solar system is 4.5 billion years old. If Titan's methane has been cycling for that entire time, something must be providing a continuous supply. Geological sources, outgassing from the interior through cryovolcanic processes, are the most conservative explanation. And there is evidence of candidate cryovolcanic features on Titan's surface. broad, shallow domes and flows that might have been produced by eruptions of water ammonia slush from the interior. If Titan's interior is warm enough, kept partially liquid by tidal heating from Saturn's gravity, then methane stored in the deep interior might percolate upward and be released at the surface over geological time. But there is another possible source, and it is the one that makes astrobiologists go quiet and pay very close attention. On Earth, one of the most prolific producers of methane is biological. Methanogenic archaea, ancient microorganisms that live in oxygen-free environments like swamps, deep sediments, and the digestive systems of animals, consume hydrogen and carbon dioxide and produce methane as a waste product. They have been doing this for billions of years. They produce a significant fraction of Earth's atmospheric methane. Could something analogous be operating on Titan, something in the methane lakes consuming available chemical energy and producing methane as a byproduct? The energy available in Titan's surface chemistry, the reaction of hydrogen with acetylene, for example, is usable in principle by a sufficiently exotic metabolism, not energy-rich by Earth standards, not comfortable, but possible. We predicted in 2005 what such life would look like, chemically, what it would do to the local environment, what signatures it would leave in the atmosphere and in the lake chemistry. And when Cassini looked, some of those signatures were present. Not proof, not even close to proof, but present. The case for life in Titan's methane lakes, exotic, improbable, radically non-Earth-like life, rests on a handful of chemical anomalies that are consistent with biology but not exclusively explained by it. The science is careful, the scientists are cautious, and the mission designed to actually look for answers, to land on Titan's surface and perform chemistry in detail that Cassini could only hint at from orbit, is already being built. We will come to that mission, but first we need to go somewhere else, somewhere smaller, somewhere colder, somewhere that, for all of Titan's intriguing chemistry, has given us even clearer, more direct, more startling evidence that the moons of Saturn may harbor something we've been searching for our entire history as a scientific civilization. Something alive. Could life exist on Titan? In 2005, two scientists at the University of Arizona published a paper. It was not a headline-grabbing paper. It did not claim to have found life. It did not make bold announcements. It did something more careful, more methodical, and ultimately more unsettling. It made a prediction. The scientists David Grinspoon and Christopher McKay asked a simple question. If life existed in Titan's methane lakes, life that used liquid methane as its solvent the way Earth life uses water, what would it need to survive? What would it consume? And crucially, what chemical fingerprints would it leave behind? Working from first principles, they identified the most likely metabolic pathway for such a hypothetical organism. The most energetically favorable reaction available in Titan's surface chemistry involves hydrogen and acetylene. Acetylene, a simple hydrocarbon present in Titan's atmosphere, can react with hydrogen to produce methane and release energy. Not much energy by Earth standards, but energy nonetheless. A Titan-adapted organism, they proposed, might consume hydrogen from the atmosphere and acetylene from the surface and produce methane as a metabolic waste product. The prediction was specific, testable, scientific, and it made two clear statements about what Cassini should observe if such life existed near the surface. First, hydrogen concentrations should be depleted at the surface, where organisms would be consuming it. Second, acetylene, which rains down from Titan's atmosphere and should accumulate on the surface, should be absent or scarce at the surface. 3 years later, Cassini's data came in. Scientists analyzing the atmospheric measurements found exactly what McKay and Grinspoon had predicted. Hydrogen concentrations did appear depleted near the surface, something was drawing it down. And acetylene, which models predicted should be abundant on Titan's surface, was essentially undetectable in surface measurements. The scientific community did not erupt in celebration. Scientists do not work that way. Instead, they got very quiet and very careful and began constructing alternative explanations. Mineral catalysts could consume hydrogen chemically without biology. Acetylene might be converted to other compounds by ultraviolet radiation before reaching the surface. The measurements might have errors, gaps, artifacts. Every alternative explanation was examined. None was definitively ruled out. None was definitively confirmed. What the community agreed on was this: the anomalies were real. The chemical signatures McKay and Grinspoon predicted were present in the data, and while biology was not the only explanation, it was not ruled out either. In the formal language of science, the hypothesis remained viable. Then, in 2015, a team at Cornell University took the theoretical case for Titan life a step further. They asked not just what Titan life would eat, but what it would be made of. On Earth, cell membranes are built from lipid molecules, fatty acids that arrange themselves into bilayers in water, forming the enclosed sacs we call cells. The hydrophobic properties of these molecules in water create the boundary between inside and outside, the essential distinction between self and environment. But lipids don't work in liquid methane. At -179 degrees C, lipids freeze solid. They lose the flexibility that makes them functional as membranes. A lipid cell membrane in Titan's methane lakes would be rigid, brittle, and useless. The Cornell team, led by Paulette Clancy and James Stevenson, asked whether any molecule could do what lipids do, but in liquid methane instead of water. After computational modeling, they found a candidate, acrylonitrile, also known as vinyl cyanide. Acrylonitrile is present in Titan's atmosphere. Cassini detected it. In computational models showed that acrylonitrile molecules could self-assemble into membrane-like structures in liquid methane, flexible, stable, capable of forming enclosed volumes. The researchers named this hypothetical structure an azotosome, a methane-based analog of the cell membrane. In 2017, astronomers using data from the ALMA radio telescope confirmed that acrylonitrile is present in Titan's atmosphere in concentrations sufficient, in principle, to form azotosome structures in the lakes below. Enough acrylonitrile exists in Titan's atmosphere to potentially populate Ligeia Mare with azotosome-based cells at a density comparable to bacteria in Earth's oceans. This is not proof of life. It is proof that the structural prerequisite for a non-water-based cell membrane exists at Titan. The ingredients are present. The energy source is available. The chemical anomalies that life would produce have been observed. Every piece of the puzzle, examined in isolation, is consistent with biology. And yet we have not gone there. Not yet. Not with the instruments needed to answer the question directly. What we know about life tells us something important. In every environment on Earth where we've looked for life, environments that seem impossibly hostile, environments that would kill a human in minutes, we have found it. The boiling, acidic waters of Yellowstone's geysers. The pitch-black, crushing depths of ocean trenches, the frozen interior of Antarctic ice sheets, the hyperarid core of the Atacama Desert. Life on Earth occupies every conceivable niche. It is not fragile. It is opportunistic, adaptable, persistent. It finds energy where energy exists and exploits it. Titan has energy. Titan has organic chemistry richer than anywhere else in the solar system, more organic molecules per square meter of surface than any other body we know of. Titan has a liquid medium, methane, that while exotic, operates on the same physical principles as water in terms of enabling chemical interactions. And Titan has had billions of years for chemistry to organize itself. The question is not whether the conditions are perfect. They aren't. The energy available per unit of chemistry on Titan is far less than on Earth. The cold slows reaction rates. The methane solvent is less chemically versatile than water. Everything works harder and slower and less efficiently. But life is not about perfection. Life is about sufficient. Sufficient energy, sufficient complexity, sufficient time. Titan has had sufficient time. But here is the complication. Even if life exists in Titan's methane lakes, exotic, methane-breathing, acetylene-consuming, acrylonitrile membrane life, proving it will be enormously difficult. The chemistry of life and the chemistry of complex non-biological organic systems overlap substantially. To distinguish one from the other requires detailed, close-up, hands-on chemical analysis, the kind that Cassini, orbiting Saturn from hundreds of thousands of kilometers away, could only approximate. The mission that could actually look, that could land on Titan's surface, scoop up material from a lake shore or a river delta, and run the detailed chemistry, is already being built. It launches in 2028. It arrives in 2034. And it carries instruments specifically designed to look for the chemical fingerprints of life that Cassini could only hint at from orbit. We will come to that mission in detail, but first we need to travel to a different moon. a moon where the evidence for habitability is not a handful of atmospheric anomalies and theoretical cell membrane analogs, a moon where the evidence is far more direct, far more complete, far more difficult to dismiss. A moon that has been shooting its own secrets into space for us to catch, and that we almost missed entirely. Enceladus and the Hidden Ocean. In 2004, when the Cassini spacecraft arrived at Saturn after 7 years of travel, mission scientists had a list of priorities. Titan was near the top. The prospect of a moon with a thick atmosphere and surface liquids was too extraordinary to ignore. The main rings were high on the list: Saturn's atmosphere, the other large moons, the magnetosphere. Enceladus was not near the top of the list. It wasn't neglected. It was scheduled for observation, of course, but it was not expected to be remarkable. It was small. It was 504 kilometers in diameter, small enough to fit comfortably within the borders of the United Kingdom. Small moons in the outer solar system are generally cold and geologically dead. They formed, cooled, froze, and sat. They do nothing. They are the outer solar system's equivalent of rubble, interesting for their records of ancient bombardment, not for any ongoing activity. Nobody expected Enceladus to be alive. In February 2005, Cassini made its first close flyby of Enceladus. The images returned were immediately puzzling. The surface was not heavily cratered, as expected for an ancient, geologically dead moon. Parts of it were smooth, geologically fresh-looking, young, as if the surface had been reshaped recently by planetary standards, by some process that had erased the impact history written in craters. Something had happened to Enceladus. Something had remade parts of its surface. Scientists put it down as curious, filed it away, and scheduled a closer look. Then came July 2005. Cassini made a much closer pass, skimming to within 175 kilometers of Enceladus' south pole, and the magnetometer, which measures the strength and direction of magnetic fields, detected something extraordinary. The magnetic field around Enceladus' south pole was being deflected, bent out of its normal configuration as if by the presence of ionized gas. Not empty space, not a dead, inert moon, a moon surrounded by electrically charged material. Something was coming off Enceladus. The instruments confirmed it. Cassini flew directly through a cloud of gas and particles emanating from the South Pole, water vapor, ice crystals, traces of other compounds, all streaming outward from a localized source on the moon's south polar region. The spacecraft literally passed through the emission. The mass spectrometer tasted it. Then the cameras turned to the South Pole, and the images that came back stopped the science team cold. Enormous plumes, geysers, were erupting from the South Polar region. Columns of material shooting upward from the surface, catching the sunlight at the edge of Enceladus' disk and glittering against the blackness of space. Not one geyser, dozens, rising from a network of long, linear cracks in the moon's south polar terrain, 4 parallel fractures, each roughly 130 kilometers long, running across the South Pole in near-perfect parallel. Scientists named them the Tiger Stripes. At the Tiger Stripes, the surface temperature was measured at -93 degrees C. On a moon where the surrounding surface sits at -200 degrees C, that 100-degree difference is enormous. The Tiger Stripes were hot, not by human standards, but hot enough to reveal that enormous amounts of heat were being released from the interior. The plumes from the Tiger Stripes were traveling at 1,400 kilometers per hour, 4 times the muzzle velocity of a rifle bullet, fast enough to escape Enceladus' weak gravity entirely and spray material into Saturn's orbit. That material, it turned out, was what was forming Saturn's E-ring, the broad, diffuse outermost ring that Cassini orbited within for much of its mission. Enceladus was feeding the ring system, a moon the size of Britain, actively manufacturing a planetary ring. But the composition of those plumes, that was the detail that mattered. Cassini's instruments analyzed the geyser material on multiple close flybys over the following decade. Water vapor, ice particles, carbon dioxide, methane, molecular hydrogen, sodium, potassium, silica nanoparticles, complex organic molecules, an inventory of chemicals that, taken together, told a specific story. To understand what story they told, you need to understand what silica nanoparticles mean. Silica, silicon dioxide, forms nanoparticles of very specific sizes under very specific conditions. When hot water, rich in dissolved silica, suddenly cools as it erupts into a cold environment. This happens in one context on Earth that is well studied and well understood: hydrothermal vents on the ocean floor. The silica nanoparticles in Enceladus plumes were, in a very real sense, smoking guns for a hydrothermal system on the floor of Enceladus Ocean. An ocean that nobody had known existed. In 2015, the case for the ocean was made definitive. Scientists analyzing Cassini's precise trajectory data over years of flybys detected a gravitational anomaly near Enceladus' south pole, a slight excess of gravity that indicated a denser-than-expected region beneath the south polar terrain. A large body of liquid water, sitting beneath an ice shell estimated at 20 to 25 kilometers thick, concentrated beneath the South Pole, but as later analysis would confirm, global. A global ocean. Beneath the entire surface of Enceladus, a liquid water ocean wraps the entire moon. Above it sits an ice shell, cracked at the South Pole, venting through the tiger stripes. Below it sits the ocean floor, possibly rocky, possibly threaded with hydrothermal vents, possibly hot and chemically active. Enceladus, this small, cold, supposedly unimportant moon, had an ocean, had hydrothermal activity, had a global body of liquid water that had, by all indications, been liquid for a very long time, long enough for chemistry to have had a chance to do something extraordinary. And then in 2017, Cassini made one more pass through the plumes, one more taste, and the mass spectrometer detected molecular hydrogen, H2, in the plumes. Molecular hydrogen is produced on Earth by a specific reaction: water reacting with rock at high temperatures in a process called serpentinization. When hot water circulates through certain types of rock, particularly rocks of the kind you'd expect to find on a small moon's ocean floor, the water and rock react chemically, producing molecular hydrogen. The presence of H2 in the plumes was therefore not just a chemical curiosity, it was an indicator of a specific process: water touching hot rock, hydrothermal activity, chemistry happening at the interface between a liquid ocean and a rocky seafloor, driven by heat from within. The silence that settled over the science team when that result came through was described by several researchers as profound. Because molecular hydrogen is not just a geological indicator, it is a food source. On Earth, at the bottom of the ocean, around hydrothermal vents, entire ecosystems exist in total darkness, independent of sunlight, independent of photosynthesis, living off the chemical energy released by reactions between hot water and rock. Microorganisms that consume H2 and CO2 and produce methane and energy. Life at the deep ocean floor, thriving on the chemistry of serpentinization, the same chemistry that Enceladus plumes appear to contain. On Earth, we discovered in 1977 that life does not need sunlight, it only needs chemical energy. And the hydrothermal vents of Earth's ocean floor, the most extreme environments we had ever considered, turned out to be among the most biologically productive environments on the planet. Enceladus has those conditions. Enceladus has liquid water. Enceladus has chemical energy. Enceladus has organic chemistry. And Enceladus has been shooting its ocean into space, free for any passing spacecraft to sample. We had not gone looking for a habitable ocean in the Saturn system. We had planned to look at the rings at Titan at the magnetic field, and instead, a tiny, insignificant-seeming moon announced itself, loudly, unmistakably, with a column of water vapor visible in photographs, as possibly the most important world in the entire solar system. The implications of what came next took years to fully process, and some of those implications are still being absorbed. The best place to find alien life. In astrobiology, the science of life beyond Earth, there is a framework, a checklist really, that researchers apply when evaluating any environment's potential to support life. It is not a complex checklist, it has 3 items. Liquid water, a source of chemical energy, organic chemistry. That's it. Those 3 conditions, appearing together in the same place, are the minimum requirements that life as we understand it requires. Every form of life on Earth, from the deepest ocean vent bacteria to the most complex human, operates on liquid water, chemical energy, and organic building blocks. We have looked at every extreme environment on Earth where these 3 conditions exist, and every single time, without exception, we have found life. Not always obvious life, not always large life, but life. Liquid water, chemical energy, organic chemistry. Let us go through the list for Enceladus. Liquid water confirmed. A global ocean beneath a 20-25-kilometer ice shell, liquid for an unknown but potentially vast span of time. Not a small body of liquid, a global ocean. Confirmed by gravitational measurements, plume chemistry, and the simple fact that those plumes are shooting liquid water into space at 1,400 kilometers per hour. Chemical energy confirmed. Molecular hydrogen detected in the plumes, indicating active serpentinization reactions between hot water and rock on the ocean floor. This is not a potential energy source. It is a demonstrated one, the same energy source that powers hydrothermal vent ecosystems on Earth, detected in the venting material of Enceladus' south pole. Organic chemistry confirmed. Complex organic molecules were detected in Enceladus plumes by Cassini's mass spectrometer. Not just simple molecules, complex ones, with molecular masses above 200 atomic mass units. Molecules of that complexity in that chemical context are typically associated with two things, either the chemistry preceding life or life itself. Both would be significant. The checklist is complete. Every box is checked. Not theoretically, not approximately, directly, physically, chemically confirmed by a spacecraft that flew through the plumes and tasted them. But there was still something missing from that checklist, something that scientists had long suspected should be there, but hadn't yet detected directly: phosphorus. Phosphorus is fundamental to life in a way that few other elements are. It is the backbone of DNA and RNA, the molecules that store and transmit genetic information. It is the essential component of ATP, the molecule that transfers energy within cells. Without phosphorus, the machinery of biology cannot function. No DNA without phosphorus. No cellular energy transfer without phosphorus. No life as we know it without phosphorus. And for years, phosphorus was the missing element in Enceladus-confirmed chemistry. Scientists expected it was there, the moon's rocky interior, by analogy with the composition of carbonaceous chondrite meteorites, should contain phosphorus minerals. But detection requires measurement, and the measurement hadn't confirmed it yet. In 2023, a team of scientists reanalyzed Cassini's mass spectrometer data in unprecedented detail. They were looking for phosphorus-bearing compounds in the plume material. The analysis was painstaking. The signals were subtle. The interpretation required careful work. But when the result came through, it was unambiguous. Phosphate, dissolved phosphate ions, detected in Enceladus plume material. Phosphorus, in a water-soluble form that chemistry and biology can use directly. Every single major chemical ingredient required for life, as we know it, has now been confirmed at Enceladus. Liquid water, chemical energy, organic chemistry, phosphorus, nitrogen compounds, carbon, hydrogen, a temperature regime at the ocean floor that, by model estimates, could support the same reactions that sustain life at Earth's hydrothermal vents. The list is complete, not almost complete, complete. This does not mean there is life at Enceladus. Science does not work by checking boxes and declaring victory. The presence of all the ingredients for a cake does not mean a cake exists. Someone has to have done the baking. The origin of life, even on Earth, remains one of the deepest unsolved problems in science. We know that it happened once. We are the evidence of that. But we don't know how likely it is, or how long it takes, or whether the conditions at Enceladus have persisted for long enough. We don't know whether Enceladus, ocean, has been liquid for hundreds of millions of years or billions. We don't know whether the hydrothermal vents are stable and long-lived or intermittent. We know that the conditions exist. We do not know whether those conditions have been seized upon. But here is something worth sitting with for a moment. The conditions for life on Earth, the early ocean, the hydrothermal vents, the chemical soup from which biology emerged, are gone. The early Earth is not accessible to us. We cannot go back and study how life began. We can only infer it from fossils and molecular biology and indirect evidence. The origin of life on Earth happened once, billions of years ago, in an environment that no longer exists. At Enceladus, that environment may still be running. Right now, today, the hydrothermal vents, if they exist, are not ancient history. They are current events. Whatever chemistry is happening at the floor of Enceladus ocean is happening at this moment, as you listen to this. If life emerged there, it didn't emerge billions of years ago and leave only fossils. It is there now in a living ocean, in a moon orbiting Saturn, accessible to a spacecraft with the right instruments. And we have a unique and extraordinary opportunity that we should not lose sight of. We don't even need to land to sample it. The ocean comes to us. Every second, Enceladus is shooting its ocean into space through those south polar plumes. Any spacecraft that passes through those plumes passes through the ejected contents of Enceladus Ocean. Cassini did this multiple times. Each flyby was, in a real sense, an ocean sample return, the spacecraft collecting material from an extraterrestrial ocean without ever landing. Cassini's instruments were not designed specifically to detect life. They were designed to do broad planetary science. Yet even with those general instruments, they detected the full chemical inventory for a habitable environment. A spacecraft with instruments specifically designed to detect biological molecules, proteins, lipids, nucleotides, living cells, flying through those plumes would have a direct chance of encountering them if they are there. Such a spacecraft is being designed. Its name is the Enceladus Orbilander. It would orbit Saturn, make multiple plume flybys to sample the ocean material, and ultimately land on Enceladus' surface near the Tiger Stripes, where freshly ejected ocean material falls back as snow, coating the surface with a record of the ocean's chemistry. If life exists in Enceladus Ocean, the Orbilander could find it. Not indirectly, not by inference, not by a chemical anomaly that requires alternative explanations. Directly, biological molecules, living cells, proof. That mission does not yet have a launch date. It is in the proposal phase, waiting for funding and prioritization within NASA's mission queue. But the scientific case for it, made stronger with every Cassini discovery, made decisive by the phosphorus detection in 2023, is essentially unanswerable. If we are serious about the search for extraterrestrial life, Enceladus is the most compelling destination in the solar system. Not because we are certain life is there, but because if we want to look somewhere that has every ingredient, every condition, and a direct delivery mechanism for ocean samples, Enceladus is the answer. And if life is found at Enceladus, if a spacecraft flying through those plumes detects a biological molecule, a living cell, a metabolism, the implications would cascade far beyond Saturn. Because Enceladus and Earth share no common history. They are separated by 1.5 billion kilometers and the entire origin story of the solar system. If life arose independently at Enceladus, then life is not a miracle. Life is not an accident. Life is what happens when the conditions are right, and the conditions are right in many places, around many stars, in many corners of the universe. A single cell from Enceladus, ocean, would not just be a biological discovery. It would be a statement about the nature of the universe. The strange dance of Saturn's moons. Saturn does not have moons the way other planets have moons. It has a system, a vast, complex, hierarchically organized system of 146 confirmed worlds, each one different, each one carrying the record of its own history, each one embedded in gravitational relationships with Saturn and with each other that have shaped their orbits, their surfaces, and in some cases their interiors. 146 moons. For perspective, Earth has 1, Mars has 2, Jupiter, long considered the moon-richest planet, has 95. Saturn has 146, and the count keeps rising as improved telescope techniques reveal smaller and smaller objects captured into Saturn's gravitational family. Many of the newly discovered moons are tiny, rocky bodies a few kilometers across, most likely captured asteroids or fragments from ancient collisions, following tilted, eccentric orbits far from Saturn in what astronomers call the irregular satellite population. They are not the dramatic worlds we've been discussing. They are the rubble of Saturn's history, witnesses to impacts and captures from the early solar system, preserved by Saturn's gravity. But the inner moons, the larger, regular moons orbiting close to Saturn in nearly circular orbits aligned with the ring plane, those are something else entirely. And among them are worlds so strange that individually, each one would merit its own documentary. Take Mimas, the smallest of Saturn's major moons, just 400 kilometers across and famous for one feature above all others, a crater. The Herschel crater, formed by an ancient impact, measures 130 kilometers across, nearly a third of Mimas' total diameter. The walls of the crater rise 5 kilometers high. At its center, a mountain rises 6 kilometers from the crater floor. The impact that created Herschel was so massive that it nearly shattered Mimas entirely. The shock waves from the impact created a pattern of fractures on the opposite side of the moon. The force of the collision focused through the moon's body and arrived at the antipode as a concentrated burst of energy, cracking the surface. The result of all this geological drama is that Mimas looks, with a startling, uncanny, impossible-to-ignore precision, exactly like the Death Star from the Star Wars films. An enormous circular structure, dark shadows suggesting an eye, sitting on a spherical gray object. The resemblance is so strong that it causes genuine cognitive dissonance when you first see it, and it is worth noting that the Death Star was designed before Voyager photographed Mimas up close. The designers of the Death Star had no idea what Mimas looked like. The resemblance is purely coincidental. The universe has a sense of humor. But Mimas has a more recent surprise than its visual resemblance to a fictional space station. In 2024, scientists analyzing data from Cassini's gravitational measurements concluded that Mimas, despite its thoroughly frozen, apparently dead appearance, likely harbors a subsurface liquid water ocean. The ocean is young by planetary standards, perhaps only 25 million years old, formed relatively recently as tidal heating from Saturn gradually warmed the moon's interior enough to melt a liquid layer beneath the ice. Mimas is what scientists now call a stealth ocean world. Its icy exterior gives no visual indication of the liquid hiding below. If confirmed, Mimas joins Enceladus in a remarkable category, Saturn's moons with hidden oceans, and it raises a question that planetary scientists are actively wrestling with. How many of Saturn's moons have liquid water interiors? How common are these hidden oceans? And if oceans are this common in Saturn's moon system, what does that say about their prevalence around other giant planets, in other star systems, throughout the galaxy? Now consider Iapetus. Discovered by Giovanni Cassini in 1671, more than 3 centuries before the spacecraft bearing his name arrived at Saturn, Iapetus is strange in a way that is immediately visible even from Earth-based telescopes. One hemisphere is as dark as coal, the other is as bright as fresh snow. Not roughly darker and roughly brighter, dramatically, almost impossibly different. The dark hemisphere, called Cassini Regio, has an albedo of about 0.03. It reflects only 3% of the light that hits it. The bright hemisphere reflects roughly 90%. The difference between them is as extreme as the difference between asphalt and fresh snow. For over 3 centuries, nobody could explain it. The leading hypothesis now involves a combination of external dust accumulation and a thermal feedback process. As Iapetus orbits Saturn, its leading hemisphere accumulates dark dust migrating inward from Saturn's outer moons, particularly Phoebe, a dark captured asteroid far out in Saturn's irregular satellite population. The leading hemisphere gets dusted. But then thermal dynamics kick in. The dark material absorbs more sunlight, gets warmer, and any volatile ices that might brighten the surface are driven off by the warming. The bright material migrates by sublimation to the cooler, trailing hemisphere where it deposits and refreezes. Dark gets darker, bright gets brighter, a positive feedback loop running over millions of years. Iapetus has another mystery that the dust theory doesn't explain at all. Running along its equator, the precise equator with extraordinary accuracy, is a ridge, a mountain range, reaching heights of up to 20 kilometers, taller than anything on Earth, taller than Olympus Mons on Mars, running for 1,300 kilometers along the equator's spine. A wall, a seam, as if Iapetus were assembled from 2 halves, stitched together at the equator, and the stitching left a visible scar. Nobody has satisfactorily explained the equatorial ridge of Iapetus. The leading hypotheses involve either the remnant of a collapsed ring system that once circled Iapetus itself, with material raining down onto the equator over millions of years, or ancient tectonic activity driven by rapid early rotation that has since slowed. Neither explanation is fully satisfying. The ridge remains one of the most visually striking and scientifically mysterious features in the entire Saturn system. Then there is Hyperion. Most moons over time become tidally locked to their parent planet, one face permanently pointing inward, one face permanently pointing outward, the moon's rotation synchronized to its orbit. Our own moon does this, we only ever see one face. The physics that drives tidal locking is well understood, and for most moons in most systems, it operates efficiently. Hyperion ignores this. Hyperion is the only known large moon in the solar system with completely chaotic rotation, not just unsynchronized, chaotic. Its rotation axis tumbles randomly in space. Its orientation changes unpredictably. It is mathematically in a chaotic dynamic state, which means that its future orientation cannot be predicted beyond a short time horizon no matter how precisely you measure its current state. It is a moon that is, essentially, always falling in a new direction. This chaos arises from the combination of Hyperion's irregular shape. It is not round, but elongated and lumpy, like a compressed sponge, and its gravitational interaction with Titan, whose large mass causes resonance effects that prevent Hyperion from settling into a stable rotation. The result is a moon that is perpetually disoriented, tumbling through space in a pattern that no calculation can pin down in advance. A moon that is, in a precise technical sense, unpredictable. And then there are the moons of the rings themselves. Pan and Atlas, tiny, irregular, potato-shaped moons orbiting in gaps within the main ring system, have accumulated ring material along their equators over time, giving them a distinctive flying saucer appearance. A clean, flat disk of accumulated ice running around their middles, deposited grain by grain over millions of years from the ring material they plow through with every orbit. They look like UFOs. They look like props from a science fiction film. They look like nothing else in the solar system. And the inner moons of Saturn, particularly the small, regular moons orbiting close to the rings, may be the youngest large objects in the solar system. Evidence from Cassini suggests that some of these moons formed from the rings themselves, from clumps of ring material accumulating gravitationally, accreting slowly into discrete objects, perhaps within the last few 100 million years. Moons that are not survivors of the early solar system, not ancient bodies of rock and ice, but newborns, created recently from the same material that once made up a lost moon and now orbits Saturn as rings. Saturn is not just a planet with moons. It is a moon factory, actively forming new worlds from the debris of an old one. And the gravitational relationships between these moons, the orbital resonances, the shepherding, the tidal interactions, create a system of extraordinary complexity and beauty. Mimas, whose large crater dominates its face, maintains the Cassini division through a gravitational resonance. Any ring particle that would orbit in the division completes exactly 2 orbits for every 1 orbit Mimas completes. Every time that ring particle would align with Mimas, it receives a small gravitational nudge, always in the same direction, always slightly pushing it away from that orbit. Over thousands of such nudges, the particles are cleared from the Cassini division entirely, leaving a gap sculpted by gravitational dynamics rather than by any physical barrier. Prometheus sculpts the F-ring, Titan's gravity destabilizes Hyperion, Enceladus' orbital resonance with Dione may be what drives the tidal heating keeping its ocean liquid. Every moon affects every other moon at some level. Every orbit is slightly shaped by every other orbit. The system is a vast, patient, gravitational clockwork, running since the solar system's formation, gradually, continuously, producing the extraordinary variety of worlds we observe today. And hidden within that clockwork, in ways we are only beginning to map, is a relationship between the moons and the planet that produces effects no one predicted, vibrations, oscillations, resonances that propagate from the moons into Saturn's rings, and from the rings into Saturn's atmosphere, and from Saturn's atmosphere into Saturn's interior. Saturn and its moons are not separate objects sharing an orbit. They are a coupled system, a gravitational symphony. And we are only now, with the full archive of Cassini's 13 years of data, beginning to hear all the instruments playing. The greatest Saturn discoveries ever made. On the morning of September 15, 2017, a spacecraft died. It did not die by accident. It did not run out of fuel unexpectedly, or suffer a catastrophic system failure, or drift beyond communication range. It died deliberately, guided by precise commands sent from Earth, following a plan that had been developed years in advance, executed with the same meticulous care that had characterized every day of its 13-year mission. Cassini, the NASA ESA-ASI spacecraft that had arrived at Saturn in 2004 and spent 13 years rewriting everything we knew about the second largest planet in our solar system, was pointed into Saturn's upper atmosphere and told to fly into it. At 6:32 a.m. Pacific time, the spacecraft began to encounter atmospheric resistance. Its thrusters fired, trying to maintain orientation, trying to keep its antenna pointed at Earth, trying to transmit data to the very last moment. For 91 seconds it fought. Then the atmosphere won. Cassini broke apart and burned, its molecules dispersing into the clouds of the planet it had studied for longer than some of the engineers in mission control had been alive. The reason for the controlled destruction was scientific and ethical. Cassini was running out of fuel. Without fuel, it would eventually become uncontrollable, an unpowered spacecraft drifting through Saturn's moon system. And if it drifted into Enceladus or Titan, it risked contaminating those potentially habitable worlds with Earth microbes that had survived the journey. 13 years in deep space does not kill all bacteria. The spacecraft that discovered Enceladus ocean could not be allowed to crash into it. The discovery was too important. The possible life was too precious to risk contaminating. And so Cassini chose, or rather, the humans who loved it chose, to sacrifice the spacecraft to protect the moons it had revealed. That moment does not belong to technical history alone. It belongs to something larger, the history of human curiosity and what we are willing to do in its service. But let's go back to the beginning. To understand Cassini's achievements, you need to understand what we knew about Saturn before it arrived, and how little that was. The first spacecraft to visit Saturn was Pioneer 11, which flew past in September 1979. It was not designed for Saturn. It was primarily a Jupiter mission that had enough trajectory flexibility to continue outward. Its instruments were relatively simple. Its flyby was fast. But it returned the first close images of the ring system and the first measurements of Saturn's magnetic field, and it survived crossing the ring plane, something engineers had genuinely worried might destroy the spacecraft. Pioneer 11 demonstrated that the region around Saturn was survivable. It opened the door. Then came the Voyagers. Voyager 1 arrived in November 1980 and Voyager 2 in August 1981. These were proper Saturn missions, spacecraft with full suites of scientific instruments, designed to make detailed observations across multiple flybys of the planet and its major moons, and what they saw changed everything. Voyager revealed that Saturn's rings were not the simple structure previously imagined. They were composed of thousands of individual ringlets, braided F-rings, unexplained spokes, and structures that varied over timescales of hours. They showed Titan's thick orange atmosphere, confirming that it was the only moon in the solar system with substantial atmospheric pressure. They photographed the strange variety of Saturn's moons, the cratered face of Mimas with its Death Star crater, the two-tone Iapetus, the smooth plains of Enceladus that suggested geological resurfacing, the chaotic Hyperion. They raised more questions than they answered, and for the next 23 years, those questions hung open, too far away, too complex, requiring a spacecraft capable of orbiting Saturn for years rather than flying past in days. Cassini was that spacecraft. Development began in the mid-1980s. The mission was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. It was enormous by spacecraft standards, 6.7 meters long, 4 meters wide, weighing nearly 6 metric tons at launch. It carried 12 scientific instruments and a separate atmospheric probe, the Huygens lander, built by ESA. It launched in October 1997 and spent 7 years traveling to Saturn, using gravitational assists from Venus twice, Earth, and Jupiter to gain the velocity needed to reach the outer solar system. When it arrived at Saturn in July 2004, it performed a critical engine burn to slow down and enter Saturn orbit. The burn took 96 minutes. If it had failed, if the engine had cut out early or fired incorrectly, Cassini would have passed through Saturn's system and continued into interstellar space, the mission over before it began. The burn succeeded. Cassini was in orbit. The science began. What followed were 13 years of continuous discovery. Let us walk through the landmarks. In January 2005, the Huygens probe separated from Cassini and descended to Titan's surface, the most distant soft landing in human history. For 2 hours and 27 minutes, Huygens fell through Titan's atmosphere, returning 350 photographs and a comprehensive chemical and physical profile of an alien sky. It revealed river channels, rounded ice pebbles at the landing site, and the chemical complexity of Titan's atmosphere in extraordinary detail. After landing, it continued transmitting surface data for 72 minutes before its battery died. In those 72 minutes, humanity had a representative on the surface of a moon of Saturn. In 2005, Cassini discovered Enceladus plumes. As described, this single discovery redirected astrobiology. The detection of liquid water, organic chemistry, and hydrothermal indicators in the output of a tiny moon elevated Enceladus from an overlooked footnote to the most astrobiologically compelling destination in the solar system. In 2006, Cassini discovered a hurricane at Saturn's south pole, a vast rotating storm with a clearly defined eye and eye wall, features previously thought to be unique to Earth's tropical cyclones. This was the first hurricane observed anywhere other than Earth, and it changed models of planetary atmospheric dynamics. In 2008, Cassini completed its initial 4-year mission and received 2 mission extensions, first the Cassini Equinox mission, then the Cassini Solstice mission, each extending its operational life and expanding its science objectives. The mission that was supposed to end in 2008 ultimately ran until 2017. Throughout those years, Cassini made repeated close flybys of Titan, more than 100 in total, building a comprehensive radar map of the moon's surface, revealing the lakes, seas, river systems, dune fields, and candidate cryovolcanic features in detail impossible from Earth. It observed Titan across nearly a full Saturnian year, documenting seasonal changes in the atmosphere, cloud systems, and surface liquid distribution. In 2013, Cassini observed a powerful electrical storm on Saturn, a superstorm, whose lightning discharges were detected as radio bursts. Scientists used these radio bursts to study the depth and dynamics of Saturn's convective storms, probing layers of the atmosphere invisible to cameras. In 2015, Cassini confirmed Enceladus global ocean, transforming a south polar anomaly into a planet-wide discovery. The same year, it made its deepest plume dive, skimming to within 49 kilometers of Enceladus' surface and directly sampling the plume material for the most comprehensive chemistry analysis of the mission. And then came the grand finale. In April 2017, Cassini began its final sequence of 22 orbits, each one threading between Saturn's cloud tops and the inner edge of the D-ring. This was a region that engineers had classified as uncertain. The density of ring particles in the gap was not well known, and the radiation environment was intense. There was a real possibility that a particle strike could disable the spacecraft before it completed the sequence. Before each grand finale ring plane crossing, Cassini pointed its large dish antenna forward, using it as a shield against particle impacts, at the cost of not being able to transmit data until after the crossing was complete. The spacecraft crossed the ring plane, collected data, emerged on the other side, turned its antenna toward Earth and transmitted 22 times, each time surviving, each time returning data from a region no spacecraft had ever entered. The data from those 22 orbits has transformed our understanding of Saturn's interior. By measuring the precise gravitational field of Saturn and the rings separately, possible only when the spacecraft was between them, scientists could determine the mass of the ring system, independent of Saturn's gravity, for the first time. The result, the rings are far less massive than anyone had calculated from a distance. Less massive means younger. The grand finale confirmed what the loss rate calculations had suggested. The rings are geologically young, hundreds of millions of years old, not billions. The grand finale also measured Saturn's atmospheric composition directly. The spacecraft was close enough for its instruments to taste the upper atmosphere, and it detected something unexpected: oxygen ions in the upper atmosphere, and complex organic molecules raining inward from the rings. The rings and the planet are chemically connected. Material cycles between them continuously. Cassini's final orbit, number 293, ended on September 15, 2017, when it entered the atmosphere and was destroyed. In 13 years, it had completed 294 orbits of Saturn, made 162 targeted flybys of 19 of Saturn's moons, returned 635 gigabytes of scientific data, and sent back 453,048 images. 453,000 images of a planet 1.5 billion kilometers away. When engineers in Pasadena lost Cassini's signal at 7:55 a.m. that morning, 83 minutes after the spacecraft entered the atmosphere, the time it took for the last signal to travel from Saturn to Earth, some of them cried. Not from grief exactly, though grief was part of it. From the particular emotion that comes when something extraordinary ends, when a chapter of human achievement closes, and you are standing in the room when the last page turns. Cassini was gone, but what it discovered, the ocean of Enceladus, the methane lakes of Titan, the young rings, the polar hexagon, the hydrothermal chemistry, the 146 moons, those discoveries remain. They have changed the questions we ask about the universe. They have changed the places we look for life. They have made Saturn not just the most beautiful planet in the solar system, but possibly the most scientifically important one. And the greatest discoveries from Saturn, they may not have happened yet. How Saturn could help us understand Earth. There is a tendency when we look outward at the solar system to treat it as separate from us, as a collection of objects to be cataloged and studied the way a museum visitor might study exhibits behind glass, interesting, beautiful, but fundamentally removed from the world outside. Saturn sits behind its glass. We observe, we photograph, we send probes, and then we return to our lives on Earth, as if what happens 1.5 billion kilometers away has no bearing on what happens here. That tendency is wrong. Saturn is not separate from Earth. It is connected to Earth in ways that are direct, measurable, and in some cases, decisive for the question of whether Earth is the kind of planet that can support complex life at all. The more closely we look at Saturn, the more clearly we see Earth's own reflection, sometimes distorted, sometimes clarified, sometimes reversed, but always illuminating. Begin with the most fundamental connection: protection. The solar system's early history was violent in a way that is difficult to overstate. In the first 100 million years after the planets formed, the inner solar system was saturated with debris, leftover planetesimals, comets deflected from the outer solar system, asteroids destabilized by gravitational interactions. The period known as the Late Heavy Bombardment, which peaked roughly 4 billion years ago, saw the inner planets, including Earth, struck repeatedly by large impactors. The Moon's heavily cratered face is a record of this era. Earth's early crust was melted, remade, and sterilized multiple times. Life on Earth emerged despite this bombardment, but the frequency and intensity of those impacts was regulated, in significant part, by Jupiter and Saturn. The gravitational influence of the two giant planets acts as a deflection system for the outer solar system. Comets and other large bodies that might otherwise follow trajectories toward the inner solar system are perturbed by Jupiter and Saturn's gravity, their orbits altered into configurations that carry them away from Earth rather than toward it. Not perfectly, some get through, as the dinosaurs learned, but statistically, the impact rate on Earth is substantially lower than it would be without the two giants patrolling the outer solar system. Saturn's contribution to this protective function is subtler than Jupiter's but still significant. Saturn's gravitational resonances with the asteroid belt, the Kirkwood gaps, the orbital patterns shaped by Saturn's periodic tugs, determine which asteroid orbits are stable and which are destabilized over time. The structure of the asteroid belt, including the rate at which asteroids are kicked into Earth-crossing orbits, is partly determined by Saturn's presence and position. Remove Saturn from the solar system in a thought experiment, and the asteroid impact rate on Earth almost certainly increases. By how much is debated, but the direction is not. Saturn also played its protective role more directly, through the grand tack. When Jupiter and Saturn migrated inward through the early solar system and then retreated outward, they did not leave the inner solar system unchanged. They swept through it, ejecting some material, compressing the rest into the asteroid belt, and in the process reducing the total mass of potential impactors in the inner solar system to a fraction of what it otherwise would have been. They cleared the road. They reduced the bombardment that Earth would face in its critical early years, the years when life was first trying to establish itself. If Saturn hadn't been there, if it hadn't formed when it did, where it did, with the mass it did, Jupiter's inward migration might have gone further. It might have disrupted the inner solar system more severely. Earth might have ended up with more mass than it does, or less. Mars might be a larger, more habitable world. Or Earth might have received so many impacts that life never gained a foothold. The precise configuration of Jupiter and Saturn, their masses, their orbital resonances, their shared history, appears to be one of the factors that made the inner solar system safe enough for life to persist. We owe Saturn some portion of our existence. But the connection between Saturn and Earth is not just gravitational. It is atmospheric, it is meteorological, it is scientific. Saturn's atmosphere, for all its alien extremes, obeys the same physical laws as Earth's. The equations that describe Saturn's jet streams are the same equations that describe Earth's jet stream, the high-altitude wind system that shapes weather patterns across the northern hemisphere. When atmospheric scientists want to test their models of jet stream dynamics under extreme conditions, conditions far beyond anything achievable in a laboratory or recreatable with Earth's own weather, they run them against Saturn's atmosphere. Saturn is, in effect, an atmospheric laboratory, an enormous, naturally occurring test chamber for the physics of planetary weather. The polar hexagon, that inexplicable, geometrically perfect six-sided storm boundary at Saturn's North Pole, has a direct analog in Earth's stratosphere. Earth's polar vortex is not hexagonal, but it is a jet stream that forms a boundary between polar and mid-latitude air masses. The same wave dynamics that create the hexagon on Saturn operate at a smaller scale, with different parameters, in Earth's atmosphere. Understanding the hexagon helps scientists understand the stability conditions for Earth's polar vortex, a system that has significant consequences for mid-latitude weather. When the polar vortex weakens or breaks down on Earth, cold Arctic air spills southward and disrupts weather patterns across North America and Europe. The physics connecting these phenomena runs through Saturn. Saturn's differential rotation, the fact that its equator rotates faster than its poles, is mirrored in Earth's oceans. Earth's ocean currents don't all move at the same speed. The surface moves differently from the deep. The equatorial regions move differently from the poles. And the mathematical description of these differential flow systems, how they develop instabilities, how they form eddies and gyres, how they transport heat, is shared between Saturn's atmosphere and Earth's oceans. Oceanographers and atmospheric scientists read each other's Saturn papers with recognition. Titan, Saturn's most Earth-like moon, offers perhaps the most direct scientific mirror. Titan's atmosphere is not Earth's atmosphere. The chemistry is different, the temperature is different, the composition is different, but the processes are the same. Atmospheric haze formation, photochemical reactions in the upper atmosphere, the development of organic chemistry in an environment with nitrogen and energy, but no oxygen. These are processes that operated on early Earth, before photosynthesis flooded the atmosphere with oxygen, before the ozone layer developed, before the chemistry of Earth's sky reached its current configuration. It went through a phase much closer to Titan's current state. Studying Titan is studying Earth's deep past. Every measurement Cassini made of Titan's atmospheric chemistry, every tholin it identified, every photochemical pathway it traced, every seasonal variation it documented, added a data point to our understanding of how planetary atmospheres develop, of how the chemistry of life's building blocks accumulates in a nitrogen-rich environment, of how organic chemistry evolves in the absence of liquid water and what it produces. And those tholins, those complex organic molecules raining down on Titan's surface, when mixed with liquid water in laboratory experiments on Earth, produce amino acids, the building blocks of proteins, the building blocks of life. The organic chemistry of Titan's atmosphere in the presence of water takes a direct step toward biology. Which raises a question of extraordinary significance. Did something like Titan's tholin chemistry operate on early Earth? Did complex organic molecules rain down on early Earth's surface from a haze-shrouded early atmosphere, providing the raw material from which life eventually assembled itself? We don't know, but Titan gives us a working model to test, a real, physical, planetary-scale experiment that we can observe and measure, that is doing chemistry similar to what early Earth may have done. Saturn's largest moon is a time machine, pointed at our own past. The connection extends even to Saturn's internal processes. The study of how heat moves through Saturn's interior, how convection operates in a world of liquid metallic hydrogen, how internal heat drives surface weather, how helium rain redistributes energy, contributes directly to our models of Earth's own interior dynamics. Earth's mantle convection, which drives plate tectonics and the cycling of carbon between the surface and the interior, operates on the same fundamental physics as Saturn's internal heat transport. The scales are different, the materials are different, but the principles are shared. In Saturn's magnetic field, that mysterious, almost perfectly aligned field that shouldn't work but does, pushes the frontiers of dynamo theory in ways that improve our models of Earth's own magnetic field. Earth's magnetic field is not perfectly stable. It has reversed polarity hundreds of times in geological history, and it is currently weakening, a possible precursor to another reversal. Understanding how planetary dynamos work, what controls their stability, what causes them to deviate from simple behavior, this is not merely academic. Earth's magnetic field protects us from the solar wind. A weakened or reversed field would significantly alter the radiation environment at Earth's surface. Understanding dynamo physics matters, and Saturn, with its paradoxically aligned field, is one of the most interesting dynamo puzzles in the solar system. Saturn is not behind glass. It is in the room with us. It has been shaping Earth's environment for 4.5 billion years, and it continues to provide the most extraordinary natural laboratory available for studying the physics that determines the fate of our own world. And that fate, Earth's fate, Saturn's fate, the fate of everything in this solar system, is not indefinite. The solar system has a future, just as it has a past, and that future includes changes to Saturn that are already underway, changes that have a timeline, changes whose first major milestone we might be able to calculate to within a few 100 million years. The rings are disappearing, and we need to talk about what Saturn looks like when they're gone. The future missions that may change everything. Science does not stop at discovery. Discovery is the beginning, the moment when a question, previously unanswerable, comes into focus as something specific, testable, and addressable. Every great discovery in the history of planetary science has done two things simultaneously: answered something, and opened the door to a question sharper and more specific than anything that came before. Cassini answered the question of whether Enceladus had an ocean. The answer was yes. The new question is there life in it? Cassini answered the question of what Titan's surface looks like. The answer was rivers, lakes, dunes, and organic chemistry. The new question is any of that chemistry biological? These are not vague philosophical questions. They are specific, scientific questions, questions to which specific, scientific answers exist, waiting to be found, and we are building the machines to find them. The first of those machines has a name that sounds like something from mythology: Dragonfly. Dragonfly is a rotorcraft lander, a spacecraft that looks functionally like a large drone. Not a rover, not a probe, not an orbiter. A drone. A flying vehicle that will land on Titan's surface, conduct science, fold its rotors, sit through Titan's long night, unfold again, and fly to a new location. Then repeat, over and over across the surface of the most Earth-like world in the outer solar system. The concept exploits something fundamental about Titan. Its atmosphere is dense, 1.5 times Earth's surface pressure, and its gravity is low, only 14% of Earth's. These two factors together mean that flight on Titan is dramatically easier than flight on Earth. Dragonfly requires only modest rotor power to become airborne. In Titan's thick air and low gravity, a drone-sized vehicle can lift enormous payloads relative to Earth and fly efficiently across the terrain. Dragonfly will fly, not hundreds of meters, not a few kilometers. It is designed to cover roughly 8 kilometers per flight, and over the course of its projected 2.7-year surface mission, it will travel more than 175 kilometers across Titan's surface. For comparison, all the planetary rovers in history combined, Sojourner, Spirit, Opportunity, Curiosity, Perseverance, have covered a combined total of less than 100 kilometers. Dragonfly will more than double that total on a single moon, in a single mission. Its target landing site is the Shangri-La Dune field near Titan's equator, an organic-rich region where complex hydrocarbon chemistry has been accumulating for billions of years. From there, it will fly toward the Selk impact crater, a site where an ancient asteroid impact melted Titan's water ice crust and mixed it with the surface organics, creating a temporary liquid water environment. A brief window, perhaps thousands of years long, during which water and organic chemistry existed together on Titan's surface. That window has long since closed. The water refroze, but the chemistry that occurred during those thousands of years, the products of water and organics mixing, is preserved in the crater's geology. Dragonfly will sample it. It will bring the most sophisticated chemical analysis instruments ever sent beyond Earth directly to the place where prebiotic chemistry most likely occurred on Titan. if amino acids formed during that impact event, if the building blocks of proteins were synthesized in that brief, warm, wet window, Dragonfly's instruments will find them. And if what formed in that crater went further than amino acids, if something more organized, more structured, more biology-like occurred, Dragonfly is designed to recognize that too. The mission launches in 2028. It arrives at Titan in 2034. The first results, the first direct chemical measurements of Titan's surface, will arrive on Earth sometime in 2035 or 2036. In roughly a decade from now, we will know more about the chemistry of Titan's surface than Cassini could tell us in 13 years of orbital observations. But Dragonfly is looking at Titan's surface, at the frozen, prebiotic chemistry of a moon whose surface temperature is -179 degrees C. If life exists on Titan, it exists in the methane lakes or possibly in a subsurface ocean. Dragonfly will look for the chemical signatures of these environments, but it won't visit them directly. For Enceladus, the calculus is different and in some ways more direct. We don't need to land to sample Enceladus Ocean. We just need to fly through its plumes, which Cassini already did multiple times with instruments that were not optimized for life detection. The mission being proposed for Enceladus takes Cassini's approach and elevates it to an entirely different level. The Enceladus Orbilander, currently in mission concept development at NASA's Jet Propulsion Laboratory, is a two-phase mission. In its first phase, it orbits Saturn and makes repeated close passes through Enceladus plumes, collecting ocean material with instruments specifically designed to detect biological molecules, not just organic chemistry, biology, proteins, lipids, nucleic acids, cell membranes, living cells. The instruments proposed for the Orbilander include a mass spectrometer capable of identifying complex biological polymers, molecules that, if found, would be essentially impossible to explain without biology. They include a microscope capable of imaging individual cells. They include fluorescence detectors sensitive to the chemical signatures of DNA and RNA. This spacecraft is not being designed to ask whether the conditions for life exist at Enceladus. That question is already answered. This spacecraft is being designed to ask whether life itself exists there, to look directly, with instruments calibrated to the task, in a place where we have every reason to look. If the Orbilander mission is approved, if it receives the funding and prioritization it requires, it would launch in the mid-2030s and arrive at Saturn in the early 2040s. The timeline is long, the costs are substantial, but the scientific and philosophical return on the investment, if the mission finds what it is designed to find, would be immeasurable. And the technology that will carry these missions is also evolving. Current spacecraft take 7 years to reach Saturn, primarily because they require multiple gravitational assists to achieve sufficient velocity. Advanced nuclear propulsion systems, nuclear thermal propulsion, which heats propellant using a nuclear reactor to achieve far greater fuel efficiency than chemical rockets, could reduce Saturn transit times to 2 or 3 years. Faster missions mean fresher spacecraft, more operational life upon arrival, and the ability to respond to discoveries with follow-on missions on timescales of years rather than decades. There's also the James Webb Space Telescope, already operational, already observing Saturn from Earth's orbit with capabilities Cassini's designers could only dream of. JWST has already detected chemical signatures in exoplanet atmospheres that would previously have required a spacecraft in orbit around those planets. Applied to Titan, JWST is beginning to provide spectroscopic data about Titan's atmospheric chemistry that complements Cassini's observations. Applied to Enceladus, it is detecting material in Saturn's E-ring, the ring that Enceladus feeds with its plumes, with a sensitivity that allows scientists to refine their models of the plume chemistry. The next generation of telescopes, enormous ground-based observatories like the extremely large telescope currently under construction in Chile, with a primary mirror 39 meters across, will add further capability. They will not replace orbital missions. Nothing replaces being there, but they extend our reach, allowing us to monitor Saturn's system continuously between spacecraft visits, watching for changes that inform the questions future missions will address. The future of Saturn exploration is not a single mission. It is a program, a sustained, progressive investigation of the most extraordinary planetary system accessible to us, carried out over decades, building from Cassini's foundation toward answers that were unimaginable a generation ago. Dragonfly flies in 2028. The Enceladus Orbilander awaits its moment. JWST watches from orbit, and somewhere in the pipeline, in the proposal documents and preliminary studies and concept papers being written right now by scientists who have spent careers studying Saturn's moons, are the missions we haven't yet named. The missions that will be designed in response to Dragonfly's discoveries. The missions that will follow up what the Orbilander finds. The story of Saturn exploration is not finished. It has barely reached its middle chapter. But even as we look forward to those missions, we must acknowledge something that the data is telling us with quiet insistence. Something about the most famous feature of the most beautiful planet. Something that has a timeline and that no mission will be able to stop. Saturn's rings are dying, and the clock is running. The day Saturn's rings disappear. Pick up a telescope, point it at Saturn. Focus carefully until the rings resolve into their full glorious detail. The Cassini division cutting its dark line between the B ring and the A ring, the inner rings fading toward the planet, the whole system tilted at an angle that shows you its full face. Look at it, remember it. Because you are looking at something temporary. Not temporary on human timescales. You will never see Saturn without rings in your lifetime, and neither will your great-grandchildren, nor the 1000th generation of your descendants. The rings will outlast every civilization and culture and nation that currently exists on Earth. In any practical human sense, the rings are permanent. They have been there for tens of millions of years, and they will be there for tens of millions more. But on the time scale of the solar system, on the scale on which Saturn itself measures its existence, the rings are a brief flash, a fleeting decoration, a transient feature of a permanent planet, and they are leaving. We know they are leaving because we have measured how fast they are leaving. Ring rain, the process by which charged ring particles are drawn downward along Saturn's magnetic field lines into the upper atmosphere, removes between 10,000 and 100,000 kilograms of ring material from the system every second. To put that in terms that feel concrete, in the time it takes to read this sentence, Saturn has lost somewhere between 40,000 and 400,000 kilograms of its rings. Gone, evaporated into the upper atmosphere, absorbed into the planet that once sacrificed a moon to create them. At this rate of loss, combined with the surprisingly small total mass of the ring system, as measured by Cassini's grand finale data, the main rings have perhaps 100 to 300 million years of existence remaining. The uncertainty in that number is large. It depends on the loss rate remaining constant, which it may not. Solar activity affects the rate of ring rain by controlling how strongly ring particles are charged. The rings may lose material faster during periods of high solar activity, more slowly during quiet periods. The timeline could shift in either direction. But the direction is fixed. The rings are leaving. There is no process that replenishes ring material at a rate comparable to the loss. Whatever catastrophe created the rings, the death of that lost moon, chrysalis torn apart by Saturn's tidal forces, was a one-time event. The material it provided is finite. It is being spent, grain by grain, second by second, in a rain of ice falling silently into Saturn's clouds. What will Saturn look like when the rings are gone? Imagine Saturn in a telescope, but without rings. It is still a giant planet, still 9.5 times the diameter of Earth, still banded in yellow and gold, still commanding an enormous retinue of moons. But without rings, it looks different. Startlingly, almost shockingly different. It looks ordinary. It looks like Jupiter with a different color scheme. The feature that makes Saturn instantly recognizable from any photograph. The feature that has made it the symbol of the solar system in art and science and culture for 4 centuries. The feature that prompted Galileo's confused amazement and Huygens' triumphant identification, will simply be gone. Through a backyard telescope, Saturn without rings would be a featureless yellowish disk. No drama, no splendor, no impossible beauty, just another large world in a dark sky. It would still be Saturn, still immense, still scientifically fascinating, still ringed by dozens of extraordinary moons. But the thing that makes Saturn Saturn, visually, culturally, emotionally, would be absent. And here is perhaps the most sobering thought in this entire documentary. We exist now. We are alive in this specific window of the solar system's history, a window that opened roughly 100 to 400 million years ago, when the rings formed, and will close 100 to 300 million years from now when they vanish. The window during which any observer anywhere in the solar system can look at Saturn and see those rings is perhaps 400 to 700 million years wide. The solar system is 4.5 billion years old. The window during which Saturn has rings represents somewhere between 9% and 15% of the solar system's total lifespan so far. An observer chosen at random from any moment in the solar system's history would most likely live in a time when Saturn had no rings. We don't live in that random moment. We live in the window, by cosmic coincidence, or by whatever word you use for the extraordinary specificity of our existence. We are the observers who get to see this. Every generation of humans who will ever live, from ancient Babylonians to whatever civilization exists a million years from now, is compressed into this narrow strip of cosmic time when Saturn wears its most spectacular feature. We are the lucky ones, the only ones who will ever see Saturn as it currently is. The E-ring, the diffuse outermost ring, fed by Enceladus plumes, has a different fate. Its persistence depends not on a long-lost moon, but on a living moon. As long as Enceladus keeps erupting, as long as the tidal heating from Saturn and the orbital resonances with neighboring moons keep Enceladus' interior warm and its ocean liquid and its tiger stripes open, the E-ring will persist. If Enceladus goes quiet, the E-ring will dissipate within decades. If Enceladus erupts for another billion years, the E-ring will still be there. The E-ring is alive in a way the main rings are not. The main rings are dying. The E-ring is breathing. And Saturn itself, beyond the rings, will persist for another 5 billion years, until the Sun expands into a red giant and the inner solar system is consumed. At that point, Saturn's fate depends on the details of the Sun's expansion. The outer solar system may survive. Saturn may persist, orbiting a cooling stellar remnant, its moons perhaps briefly warmed by the red giant's luminosity into something approaching habitability, a temporary reprieve, an unlikely last chapter. But all of that is extraordinarily far away. On any human timescale, Saturn is eternal, its rings are not. There is something beautiful about that, something that invites a kind of attention that permanence does not. The rings are precious not despite their impermanence, but because of it. They are here, they are now, and like everything fleeting in the universe, they deserve to be seen while they can still be seen. Look up at Saturn tonight if the sky allows it. Find it, it is bright enough to see with naked eyes, yellowish, not twinkling the way stars do. Point any telescope at it, any telescope. A $50 department store refractor will show you the rings. And remember when you see them that you are one of the small fraction of all possible observers, across all of time, who gets to see them at all. But before we end, before we reach the final revelation that this entire documentary has been building toward, we need to do one more thing. We need to go there. We need to close our eyes and actually arrive at Saturn, not as data, not as numbers, as humans, as creatures of sense and experience. We need to feel what it would actually be like to stand in the presence of the most extraordinary place within reach of our civilization. Because no number conveys what a place is, only being there does. And while we cannot go there yet, the being there is still ahead of us in the future. For some generation not yet born, we can try. We can approximate. We can use everything we know to build the closest thing to the experience. Come with me. What humans would experience near Saturn? You have been traveling for 7 years. 7 years in a spacecraft, a vessel smaller than a city bus, moving through a void so complete and so cold and so utterly without reference that the word empty doesn't capture it. 7 years without weather, without the smell of rain, without the change of seasons. 7 years of watching the sun shrink from the blazing disk that lights your world to a star that is bright but contained, that you could comfortably glance at through a filter that provides light without warmth. And then Saturn appears on the approach cameras, not as a point of light anymore, not as the yellowish star you'd spot in an Earth sky, as a disk, ringed, unmistakable. Your first coherent thought is that the photographs lied, not because they were wrong, they were accurate, but because no photograph has ever conveyed scale. The rings, as Saturn grows in your cameras during the final approach, do not look like a band. They look like a plane, an infinite horizontal plane of light extending from the planet to the edges of your camera frame and beyond. Tilted toward you at an angle, catching the dim but still present sunlight from 1.5 billion kilometers away and scattering it in every direction. The rings are not around Saturn the way a ring is around a finger. They are around Saturn the way an ocean is around an island. They are the dominant feature. They are what you see first. They are what you keep seeing. You enter orbit, you cross the ring plane. In the fraction of a second it takes to pass through the rings at orbital velocity, you are surrounded by a horizontal curtain of ice particles ranging from dust to boulders, spread impossibly thin across an impossibly wide disk, glittering at the edges of your visual field. Then it is over, you are through. Below you, or what your brain insists on calling below, even in weightlessness, Saturn fills more of your sky than you expected, more than the moon fills Earth's sky. Saturn is not the backdrop, it is the environment. The colors are not what the photographs suggested. Saturn's cloud bands are subtler in person, muted yellows, soft ochres, pale creams, but the transitions between them are sharper than any photograph conveys, with fine structure at the boundaries of each band that speaks of immense wind shear and enormous atmospheric dynamics. The hexagon at the North Pole is visible from orbit, and seeing it, actually seeing a geometrically perfect six-sided polygon on the face of a planet, does something to the brain that photographs don't replicate. You keep looking at it. You keep waiting for it to resolve into something less regular, something more natural looking. It doesn't. It is exactly as perfectly hexagonal as the data said it was. You descend toward Titan first. Entering Titan's atmosphere is not like entering Earth's. Earth's atmosphere resists. There is deceleration, there is heat, there is the violence of a body moving at orbital velocity through a thickening medium. Titan's atmosphere does the same, but differently. The thick, dense nitrogen-methane air grips the spacecraft firmly, slowing it. And as the deceleration reduces to something manageable, and your vehicle levels out into controlled descent, you look out the window. Orange, everything is orange. Not the orange of a sunset, a persistent, all-encompassing, sourceless orange glow. The haze is everywhere, diffusing the dim sunlight into a uniform amber that fills the sky from horizon to horizon. You cannot see the sun. You cannot see the stars. You cannot see Saturn, though you know it hangs somewhere above you, larger than the full moon appears from Earth. You see only the haze, and below it, slowly resolving, the surface. The surface of Titan comes up in stages. First, a flat darkness below the haze, undefined, directionless. Then, as you descend further and the haze thins slightly, features emerge. You can see where the dunes begin, enormous parallel ridges of dark organic material, stretching away to the horizon in a pattern eerily reminiscent of a desert scene from a low-flying aircraft. The surface is not hostile-looking. It is strange as this is to say about a world at -179 degrees C, a world whose rain is natural gas, a world that would kill you instantly without protection. It is almost serene. You land near a methane lake shore. You look through the window at a liquid surface that stretches to the horizon with almost perfect stillness. No waves, no ripple, a mirror of dark liquid, methane and ethane, reflecting the orange sky above with a clarity that seems impossible. Rocks of water ice, smoothed by ancient methane rivers, scatter the foreground. The sky glows amber. It is quiet in a way that is distinct from Earth quiet, a denser, more muffled quiet, the sound-absorbing thickness of the air producing a silence that feels physical. If you stepped outside, if you wore a suit that provided oxygen and thermal protection, nothing more, the first thing you would notice is the air pressure, slightly more than Earth's, pushing gently against your suit from every direction. Dense air, you could feel it almost. The second thing you would notice is the gravity, only 14% of Earth's. You would be almost floating. Each step would be a slow, exaggerated bound. The equipment on your back, heavy on Earth, would feel almost weightless. And if someone had brought wings, actual physical wings, strapped to your arms, Titan's thick air and low gravity would let you fly. Human-powered, arm-flapping flight. On Titan, it is theoretically possible. The third thing you would notice is the light, or rather the quality of the light. It is not dark. Titan's thick atmosphere diffuses the sunlight into a general glow that is brighter than a cloudy Earth day, but directional shadows are absent. There is no clear sun direction. The light comes from everywhere and from nowhere. It is the light of an overcast world, but amber rather than gray. You leave Titan, you travel to Enceladus. Enceladus is a world of white, absolute, almost painful white, the most reflective large surface in the solar system, reflecting 99% of the light that hits it, glittering in the dim Saturnian sunlight like a newly polished mirror. From orbit, it looks almost artificial, too regular, too smooth, too bright. and then the South Pole comes into view. The plumes are visible. Even from orbit, they are visible columns of material rising from the tiger stripes and expanding into space, catching the sunlight and glittering against the blackness beyond the moon's limb. Dozens of individual jets, merging into a broader plume that extends hundreds of kilometers above the surface before the particles either escape Enceladus, gravity entirely, or begin the long arc back to the surface as gently falling snow. If you descended to the surface near the tiger stripes, you would feel the heat, not warmth by human standards, but a detectable difference from the surrounding -200°C surface. You would stand in a landscape of cracked and striated ice, the tiger stripes running in parallel lines across the terrain before you, steam, water vapor, rising from the fractures and catching the light. You would be standing on the roof of an ocean. Below your feet, through 20 kilometers of ice, a global ocean of liquid water would be circulating, its chemistry stirred by hydrothermal vents on its floor, its secrets, still unread, waiting. Above you against the blackness, Saturn would hang. This is the view. This is the view that no human has ever seen and that some human will one day see. Saturn, from the surface of Enceladus, fills a significant arc of sky, not overwhelming, not as large as you might expect given the distance, but unmistakable and extraordinary. The rings, viewed edge-on from the ring plane in which Enceladus orbits, appear as a thin, brilliant line drawn across Saturn's equator, not the face-on view we see from Earth, but an edge, a razor-thin plane of light bisecting the planet horizontally. Below the ring line, Saturn's southern hemisphere glows in subtle banded colors. Above, the north and the hexagon, visible as a subtle six-sided pattern in the cloud structure if you know what to look for. The radio emissions of Saturn, converted to audio by your instruments, fill your headset, not static, not the hiss of solar wind, a complex, shifting, cycling chorus. Low notes and high notes, rising and falling in patterns that repeat roughly with Saturn's rotation. The planet is singing, in a frequency no human ear can detect without instruments, but real, measurable, continuous. Saturn has been singing this song for as long as it has had a magnetic field, for billions of years, to no audience, to the empty space of the outer solar system. You are the audience now. You return to orbit, you watch Saturn from above. You watch the shadows of the moons move across the ring's surface, dark circles sliding silently across the glittering ice. You watch the rings thin to invisibility as your viewing angle changes, then resolve again into their full majesty as you orbit around. You watch a storm system in Saturn's northern hemisphere, a bright white cluster of convective cells building, growing. You watch it spread. And you feel something that has no precise English word, the feeling of being completely, utterly, immeasurably small in the presence of something that does not notice you. Not hostility, not malevolence, just scale. Saturn does not know you are there. It does not know you exist. It has been here for 4.5 billion years without you, and it will be here for billions more. You are a visitor, a brief, fragile, astonishing visitor, the product of 4.5 billion years of planetary evolution and biological accident and cultural history, floating in a spacecraft around a planet that dwarfs every category you were born into. And yet you built the spacecraft, you calculated the trajectory, you figured out how the hexagon works mostly, you detected the ocean, you tasted the plumes, you found the phosphorus, you understood what the rings are made of, where they came from, and how long they will last. Something 4.5 billion years old, in the presence of something 400,000 years old. And the young thing, the small, fragile, brief thing, understood the old one. That perhaps is the most extraordinary fact of all. But there is one more, one final discovery, one revelation that we have been building towards since the first chapter, through every storm and every moon and every geyser and every ring. One fact about Saturn that, when you truly absorb it, changes how you think about planets, about matter, about what it means for something to be solid. We are almost there. The most astonishing Saturn fact ever discovered. We began this journey with a fact that seemed like a punchline. Saturn floats. It seemed like a curiosity then, a charming, counterintuitive party trick for the most visually dramatic planet in the solar system. Enormous but weightless, majestic but buoyant. We accepted it as a quirk of Saturn's composition and moved on to other things, the storms, the hexagon, the rings, the moons, the hidden oceans. But we are coming back to it now, because that fact, Saturn's impossible lightness, was not a curiosity. It was a clue, It was pointing towards something about Saturn's interior that we only confirmed within the last decade, using data from Cassini's final months, and that has quietly rewritten our understanding of what a planet actually is. For most of the history of planetary science, we imagine the interiors of planets in layers. Distinct layers, like the layers of an onion, each one different in composition and state, each one with a reasonably sharp boundary where one layer ends and the next begins. Earth has a crust, a mantle, an outer core, an inner core. Jupiter and Saturn, by analogy, were assumed to have a rocky icy core, dense and compact, sitting at the center like a stone inside a peach, surrounded by layers of metallic hydrogen and then molecular hydrogen gas, each transition reasonably sharp. This model was elegant, it was intuitive, it matched theoretical calculations, and for decades nobody had the means to test it directly. Cassini's grand finale changed that. As the spacecraft threaded between Saturn and its rings on those final 22 orbits, it was doing something more than collecting ring data and atmospheric samples. It was listening to Saturn, not to radio emissions or magnetic signals, but to something subtler and more revealing, the oscillations of the rings. Saturn, like any large body with an internal structure, vibrates. The planet rings in the physics sense like a bell. Different layers of its interior move, oscillate, slosh at different frequencies, and those oscillations propagate outward through the planet and eventually reach the rings, where they leave detectable imprints. Spiral density waves, patterns in the ring material that radiate outward from the planet at specific locations, are driven by the resonances between the rings and Saturn's internal oscillations. By mapping these density waves in extraordinary detail during the grand finale, scientists could work backwards from the ring patterns to infer the structure of Saturn's interior. What they found was not layers. Saturn's core is not a compact, rocky sphere sitting cleanly at the center of the planet. It is a vast, diffuse, gradual structure that extends through roughly 55% of Saturn's total radius, more than half the planet from center to cloud top. Not a stone inside a peach, not even a stone, something more like a very thick soup, a gradual blend of rock, ice, and gas, all mixed together, with composition and density changing smoothly from the center outward, rather than jumping sharply at defined boundaries. Scientists called it a fuzzy core, and the name, while informal, is precise in its implications. Saturn's core is fuzzy, it does not have edges, it does not have the clean, sharp boundaries that models assumed. It transitions seamlessly, continuously, over thousands of kilometers from whatever sits at the very center outward into the metallic hydrogen layer above. And that fuzzy core appears to still be mixing. 4.5 billion years after Saturn formed, material in its interior has not fully settled. Dense material has not completely separated from lighter material. The interior of Saturn is still in a process of slow, geological differentiation, still sorting itself out, still in motion, still incomplete. In a very real sense, Saturn's interior is not finished. Think about what that means. The second largest planet in the solar system, 4.5 billion years old, is still forming. Not its atmosphere, not its rings, not its moons, its interior, its core. The fundamental structure of the planet itself is still in process, still becoming what it will eventually be, over timescales that dwarf the entire history of complex life on Earth. The fuzzy core also connects to the magnetic mystery. Saturn's almost perfectly aligned magnetic field, the one that shouldn't exist according to dynamo theory, may be a consequence of the fuzzy core structure. If the boundary between the core and the metallic hydrogen layer above is gradual and diffuse rather than sharp, the convective flows that generate the dynamo may be organized differently from anything our models assumed. The fuzziness may be what smooths out the magnetic field. The lack of a sharp boundary may be what produces the paradoxically symmetric field. The mystery may not be a mystery at all, just the consequence of a core that doesn't behave the way we assumed cores behave. But the fuzzy core's implications extend far beyond Saturn, because Saturn is not the only planet with a fuzzy core. When scientists applied the same techniques to existing data from Jupiter, where the Juno spacecraft had been making similar measurements, they found the same thing. Jupiter's core is also fuzzy, also diffuse, also gradual. The two largest planets in our solar system, the two bodies that have most profoundly shaped the solar system's architecture and the prospects for life on Earth, both have interiors that are fundamentally different from what we assumed. And if that's true of Jupiter and Saturn, it may be true of giant planets throughout the galaxy. Every exoplanet we've observed, every gas giant orbiting another star, may have a fuzzy core. Our models of how planets form, how they age, how their interiors evolve, all of them need to be revised. The discovery was not just about Saturn. It was about the physics of planets, about what a planet is. We have spent 4.5 billion years orbiting a star alongside Saturn, watching it from a distance that diminished to nothing compared to the size of the galaxy. And in the last 50 years of serious exploration, in the span of a single human lifetime, we have discovered that it harbors hidden oceans. Active geysers, alien chemistry, liquid hydrocarbon seas, the conditions for life, geological features that defy mathematical expectation, and a fuzzy interior that is still, quietly, slowly becoming what it will one day be. In 50 years, we went from not knowing the length of Saturn's day, still not fully resolved, to knowing that the most famous planet in the solar system has a core without edges. From not knowing that Enceladus existed as anything more than a small cold moon, to knowing that it has a warm, chemically rich ocean with every ingredient required for life. From thinking of Titan as a curiosity, to understanding it as a mirror of Earth's own past, a laboratory for the chemistry that may have preceded life on our own world. What will the next 50 years add? We are sending Dragonfly to Titan in 2028. We are developing the Enceladus Orbilander. We are already observing Saturn with the James Webb Space Telescope. Future missions will go deeper, into the plumes, onto the surfaces, through the rings. And the questions they will carry are sharper than any before. Not what is Saturn made of, but is Saturn's ocean moon alive? Not do the conditions for life exist, but does life exist? Not what are the rings, but what do they tell us about the formation of planets everywhere? These are questions that matter beyond Saturn, because Saturn is not the point. Saturn is the location. The point, the real point, is the question behind all of planetary science, behind all of astronomy, behind the entire multi-billion-year narrative of matter organizing itself into stars and planets and moons and oceans and chemistry, and possibly life. Are we alone? Saturn's moons may hold the answer, not the confirmed answer, not yet, but the closest we have ever come, the most direct pathway we have ever found, the most compelling destination we have ever identified, and we are building the machines to go there. Slowly, imperfectly, underfunding pressure and political uncertainty and the ordinary difficulties of doing extraordinary things, but building them nonetheless. There is a spacecraft called Voyager 1 that left the solar system entirely in 2012. It passed Saturn in 1980, returning the first close images of the rings and the hexagon. Then it kept going. It is now more than 23 billion kilometers from Earth, further from us than any human-made object has ever been, still transmitting, still returning data, still operational after 47 years of continuous operation. On board is a golden record, a phonograph record covered in gold to resist corrosion, containing sounds and images of Earth, music, languages, animal calls, ocean waves, a child laughing, a message in a bottle thrown into an infinite sea. The designers of the Voyager record were working from a specific hope, that somewhere, at some point, something might find it. Something capable of understanding a phonograph record, something with the curiosity to look at it, the intelligence to decode it, and the recognition to understand what it contains. We do not know if such a thing exists. We do not know if we are alone in this universe of 200 billion trillion stars and their uncountable planets and moons. We do not know if life arose once here, improbably, against all odds, or whether it arises wherever the conditions allow, as naturally and inevitably as stars form from collapsing nebulae. But we are closer to knowing than we have ever been, the closest we have ever been, and the distance between us and that answer is measured not in light years, but in kilometers, 1.5 billion kilometers to be approximate, to a small, cold, impossibly active moon, barely larger than Britain, shooting its ocean into space at the speed of a rifle bullet. If Enceladus is alive, if there are microorganisms at this moment living in the heat and chemistry of its ocean floor, metabolizing hydrogen, producing methane, cycling through whatever passes for a biological rhythm in minus 193 degrees C water beneath 25 kilometers of ice, then we are not alone. And we never were. Life is not the exception. Life is the rule. And the universe, all of it, every hydrogen atom and every carbon chain and every rocky planet and every icy moon has been quietly, patiently, relentlessly practicing at becoming something aware. We are one result of that practice. Enceladus, perhaps, is another. Saturn has been in this solar system for 4.5 billion years. For most of that time, there was no one to see it. No eye to catch its rings catching the sunlight. No mind to wonder about its hexagon, or be amazed by its storms, or recognize that behind the beauty and the scale and the violence of the weather there might be something small and warm and alive, waiting beneath the ice of a tiny moon in the outer dark. Now there is. We are here, we noticed, we looked. We built instruments sensitive enough to taste an ocean we had never visited, and we found the ingredients for life, and we are building the machines to go back and ask the final question. That is what it means to be human in this particular century, to be the species that looked at the most beautiful planet in the solar system and saw not just beauty, but a question, not just a question, but a method, not just a method, but a mission. The rings will disappear in 100 million years, the moons will evolve, Saturn's fuzzy core will continue its slow differentiation, the sun will eventually expand, and the outer solar system will change in ways beyond our current imagination. But right now, in this sliver of cosmic time, in this brief, astonishing window, the rings are here, the oceans are here, the plumes are here, the chemistry is here. And so are we. We are here to see it, we are here to understand it, and we are here, standing at the very beginning of the answer to the oldest question any conscious being has ever asked, to find out whether, in the vast and mostly silent universe, anyone else is here too. Look up at Saturn tonight. It is one of us.